Tonight, we're going to explore one of the most fascinating mysteries in our solar system. We're going to discover why Venus, a planet almost identical to Earth in size and composition, became a hellish inferno while our world flourished with life. By the end of this journey, you'll understand how a planet can transform from potentially habitable to utterly hostile, and what that transformation means for our own world. Before we begin, if you enjoy these deep explorations of space and planetary science, a quick like or subscribe would really help the channel grow. Now let's embark on our journey to Earth's closest planetary neighbor, the planet that went catastrophically wrong, the brightest light in our sky. Look up on almost any clear evening or morning, and you'll likely see Venus. After the sun and moon, it's the brightest natural object in our sky. The ancient Romans named it after their goddess of love and beauty, captivated by its brilliant white appearance as it hung in the twilight sky. The Greeks knew it by two names, believing they were observing two different celestial bodies: Phosphorus, the morning star that heralded the dawn, and Hesperus, the evening star that followed the sunset. They eventually realized these were the same wandering light, a single planet that seemed to chase the sun across our sky. Venus shines so brightly because it reflects an enormous percentage of the sunlight that strikes it. About 70% of incoming solar radiation bounces back into space from its thick cloud deck, giving Venus the highest albedo of any planet in our solar system. This reflectivity makes it visible even in broad daylight if you know where to look. Before the advent of accurate navigation instruments, sailors and travelers relied on Venus as a guiding light in the pre-dawn and post-sunset hours. Ancient civilizations tracked Venus's movements with remarkable precision. The Maya built elaborate astronomical observatories and developed complex calendar systems based partly on Venus's cycles. They knew that Venus appeared to trace a pentagram pattern in the sky over an 8-year period, completing 5 synodic cycles as Earth completes 8 years. The Babylonians recorded detailed observations of Venus on clay tablets dating back more than 3,000 years, noting its positions against the background stars with impressive accuracy. For centuries, Venus remained mysterious. Through even the most powerful telescopes, observers could see only an unbroken expanse of yellowish-white clouds. No surface features were visible. Some astronomers reported faint markings in the cloud tops, but these changed so rapidly that determining the planet's rotation rate proved impossible using visual observations alone. The clouds told us nothing about what lay beneath. In the early 20th century, as spectroscopy became a powerful tool in astronomy, scientists began analyzing the light reflected from Venus's clouds. They found strong absorption bands, indicating the presence of carbon dioxide, though they couldn't yet determine how much. Some speculated that Venus might be a steamy jungle world, its thick clouds the result of vast oceans evaporating under a hotter sun. Others imagined it as a desert planet, or perhaps a global ocean with no dry land. Science fiction writers of the 1930s and 1940s frequently set adventures on Venus, depicting it as a lush, swampy world teeming with primitive life. The truth, when it finally emerged, shocked everyone. In 1956, radio astronomers detected microwave emissions from Venus that indicated extremely high temperatures, far hotter than anyone had predicted. These observations suggested surface temperatures exceeding 600 degrees Fahrenheit, hot enough to melt lead. many scientists were skeptical. The measurements seemed too extreme to be real. How could a planet covered in clouds be that hot? The answer came from an unlikely source. In 1962, the Mariner 2 spacecraft flew past Venus at a distance of about 21,600 miles. Its instruments confirmed the radio observations. Venus's surface was indeed hellishly hot. The mission also discovered that Venus rotated incredibly slowly and in the opposite direction from most planets. This retrograde rotation meant that on Venus, the sun rises in the west and sets in the east. The planet's day was extraordinarily long, though the exact period wouldn't be determined with precision for several more years. Ground-based radar observations in the early 1960s finally measured Venus's rotation rate with certainty. The planet takes 243 Earth days to complete one rotation on its axis. Surprisingly, this is longer than Venus's orbital period of 224.7 Earth days. A day on Venus is longer than its year. This bizarre relationship between rotation and revolution is unique in the solar system. The combination of the retrograde spin and the orbital motion means that a solar day on Venus, from one sunrise to the next, lasts about 117 Earth days, roughly half a Venusian year. The radar observations also began to penetrate the clouds, revealing the first hints of Venus's hidden surface. The planet appeared to have relatively flat terrain with some highland regions, but the resolution was limited. To truly understand Venus, spacecraft would need to visit in person. Earth's twin sister, Venus and Earth, are often called twin planets, and with good reason. Stand them side by side, and the resemblance is striking. Venus has a diameter of 12,104 kilometers, only 638 kilometers less than Earth's 12,742 kilometer diameter. That's a difference of just 5%. In the vastness of space, where planets range from tiny Mercury to gas giants hundreds of times Earth's size, Venus and Earth are remarkably similar. The mass comparison is equally close. Venus weighs in at about 82% of Earth's mass. This similarity in both size and mass means the two planets have nearly identical densities, around 5.2 to 5.5 grams per cubic centimeter. Density tells us about composition. Both planets are made of the same basic materials: an iron-nickel core surrounded by a rocky silicate mantle and crust. They're both terrestrial planets, rocky worlds fundamentally different from the gas and ice giants of the outer solar system. The internal structure of Venus, inferred from gravity measurements and models, mirrors Earth's layered architecture. At the center lies an iron-nickel core, roughly 3,000 kilometers in radius. This core is likely partially molten, though we can't be certain without seismic data. Surrounding the core is a silicate mantle, extending up to within 50 to 100 kilometers of the surface. The mantle is solid rock, but at the enormous pressures and temperatures of planetary interiors, rock behaves plastically over geological timescales, flowing like a very viscous fluid. Convection currents in the mantle drive geological activity at the surface. The outermost layer is the crust, the thin solid shell on which geological features form. Venus's crust is estimated to be 20 to 50 kilometers thick. On average, similar to Earth's continental crust, it's primarily basaltic in composition, based on measurements taken by Soviet landers. Basalt is a dark volcanic rock rich in iron and magnesium, the same material that forms Earth's oceanic crust and many volcanic islands. Despite these profound similarities, Venus and Earth have taken radically different paths. The most obvious difference is the lack of water. Earth's surface is 71% ocean, and water permeates our world, shaping everything from weather to geology to life itself. Venus is bone dry. Its atmosphere contains only trace amounts of water vapor, and its surface is utterly desiccated. If Venus ever had oceans, they vanished billions of years ago. Another crucial difference is the absence of a global magnetic field on Venus. Earth's magnetic field, generated by the motion of liquid iron in our outer core, shields us from the solar wind and cosmic radiation. The field extends tens of thousands of kilometers into space, creating a protective magnetosphere. Venus has no such protection. Its magnetic field is incredibly weak, essentially non-existent. The planet does have an induced magnetic field where the solar wind interacts with its upper atmosphere, but this provides minimal shielding. Why does Venus lack a magnetic field? The generation of a planetary magnetic field requires three things: a conducting fluid core, convection to drive circulation of that fluid, and sufficient rotation to twist the convective motions into organized patterns. Earth's relatively rapid rotation, completing a full turn in 24 hours, helps organize the convective flows in our outer core. Venus's incredibly slow rotation, taking 243 Earth days, may not provide enough Coriolis force to generate a sustained dynamo. Additionally, if Venus's core is not actively convecting, perhaps because the planet has cooled differently than Earth, no dynamo would operate regardless of rotation rate. The lack of a magnetic field has consequences. The solar wind, a stream of charged particles flowing from the sun, strikes Venus's upper atmosphere directly. Over billions of years, this bombardment has stripped away significant amounts of atmospheric gas. Lighter elements like hydrogen escape more easily. This atmospheric erosion is one reason Venus has lost whatever water it once possessed. Without a magnetic shield, water molecules in the upper atmosphere get broken apart by solar ultraviolet radiation, and the liberated hydrogen atoms escape to space. Surface gravity on Venus is 91% that of Earth. If you could stand on Venus's surface, you'd feel slightly lighter than on Earth, but the difference would be barely noticeable. This similarity in gravity is another consequence of the similar mass and size. Escape velocity, the speed needed to leave the planet entirely, is 10.36 kilometers per second on Venus compared to 11.2 kilometers per second on Earth. The planet's gravity is strong enough to hold onto a thick atmosphere, as we'll explore shortly. Venus orbits the Sun at an average distance of 108 million kilometers, or 0.72 astronomical units. Earth orbits at 150 million kilometers, or 1 AU by definition. Venus is about 28% closer to the Sun, receiving roughly twice as much solar energy per square meter as Earth receives. This proximity matters enormously for understanding Venus's climate. The closer orbit means Venus completes its journey around the Sun more quickly. A Venusian year is 224.7 Earth days. Interestingly, Venus's orbit is the most circular of any planet in the solar system. Its orbital eccentricity is less than 0.01, meaning the orbit is nearly a perfect circle. Earth's orbit, by comparison, has an eccentricity of 0.017, resulting in a slight variation in our distance from the Sun over the course of a year. Venus receives essentially the same amount of sunlight year-round, with no seasonal variations, caused by orbital eccentricity. The planet's axial tilt is tiny, only 2.64 degrees from perpendicular to its orbital plane. Actually, if we account for the retrograde rotation, Venus's axial tilt is 127.4 degrees, but the effect is the same. The planet has almost no seasons. Earth's 23.5-degree tilt gives us pronounced seasonal variations, as different hemispheres tilt toward or away from the sun during our year. On Venus, the sun's path across the sky remains nearly constant throughout its long year. Combined with the thick atmosphere that distributes heat globally, this means temperature varies little from equator to poles or from one time of year to another. Looking at these characteristics, the early similarity to Earth becomes even more striking. Two rocky planets, similar in size, mass, and composition, forming in adjacent regions of the same protoplanetary disk around the same star from the same primordial materials. They should have evolved similarly. Yet today, Earth is a vibrant world of oceans, continents, diverse climates, and abundant life, while Venus is a scorched wasteland shrouded in acid clouds. Understanding what caused these divergent outcomes is one of the central questions in planetary science. The atmosphere of hell. To understand Venus's transformation into an inferno, we must examine its atmosphere in detail. This is where the planet's hellish nature becomes unmistakably clear. Venus's atmosphere is not merely dense, it's crushing. At the surface, atmospheric pressure reaches 93 bars, or 93 times the pressure at sea level on Earth. To experience equivalent pressure on Earth, you'd need to descend about 900 meters below the ocean's surface. At that depth, the weight of water above creates immense pressure. On Venus, this pressure exists at the ground level, created by the sheer mass of atmosphere piled above. The composition is equally extreme. The atmosphere is 96.5% carbon dioxide. The remaining 3.5% is mostly nitrogen, with trace amounts of sulfur dioxide, water vapor, carbon monoxide, argon, helium, and neon. For comparison, Earth's atmosphere is 78% nitrogen, 21% oxygen, and less than 1% argon, with CO2 making up a mere 0.04%. The concentration of CO2 on Venus is more than 2,000 times higher than on Earth. This carbon dioxide creates a greenhouse effect of staggering intensity. Greenhouse gases allow visible sunlight to pass through, but trap infrared radiation trying to escape back to space. Carbon dioxide absorbs infrared radiation very effectively. On Earth, our small percentage of CO2 keeps our planet about 33 degrees Celsius, warmer than it would be without any greenhouse effect. On Venus, with nearly pure CO2 at immense pressure, the greenhouse effect is amplified beyond imagination. The result is a surface temperature of 464 degrees Celsius, or 867 degrees Fahrenheit. This is hot enough to melt lead, zinc, and tin. It exceeds the melting point of many metals. More startling, this temperature is hotter than Mercury's surface, even though Mercury is significantly closer to the Sun. Mercury receives more than 4 times as much solar energy as Venus, yet its maximum surface temperature is only about 430 degrees Celsius. Venus's thick atmosphere traps heat so effectively that it becomes hotter than any other planet in the solar system. The temperature is remarkably uniform across Venus's surface. There's essentially no difference between day and night temperatures, despite the fact that Venusian nights last about 58 Earth days. The thick atmosphere circulates heat so efficiently that even the night side remains at 464 degrees. There's also minimal temperature difference between the equator and the poles, again due to atmospheric circulation. The entire surface is an oven, uniformly baked to the same extreme temperature. At these temperatures and pressures, the atmosphere near the surface enters a supercritical state. Carbon dioxide becomes supercritical at 31 degrees Celsius, and 73.8 bars. Venus far exceeds both thresholds. Supercritical fluids have properties intermediate between gases and liquids. They can diffuse through materials like gases, but have densities closer to liquids. The lowest layer of Venus's atmosphere, in contact with the surface, is a supercritical fluid of carbon dioxide and nitrogen. This creates bizarre conditions unlike anything found naturally on Earth. Rising through the atmosphere, pressure and temperature decrease. At an altitude of about 50 kilometers above the surface, conditions become surprisingly benign. Here, the temperature is around 60 degrees Celsius, and the pressure is about 1 bar, similar to Earth's sea level pressure. This region of Venus's atmosphere in the lower cloud layers is actually the most Earth-like environment in the solar system beyond Earth itself. It's more hospitable than Mars, where the thin atmosphere provides minimal pressure and temperatures regularly drop below -100 degrees Celsius at night. This relatively comfortable zone has led to proposals for floating habitats or colonies that could float in Venus's atmosphere. Breathable air, a mixture of nitrogen and oxygen, has lifting power in a CO2 atmosphere. A habitat filled with Earth-like air would naturally float at this altitude, requiring no active lift. Protected inside such a habitat with proper shielding and cooling systems, humans could potentially survive more easily in Venus's atmosphere than on the surface of Mars. The concept remains speculative, but it illustrates the strange dichotomy of Venus: nightmarishly hostile at the surface, yet almost welcoming 50 kilometers up. The clouds themselves are another extreme feature. Venus's clouds are not water clouds like those on Earth. They're composed primarily of concentrated sulfuric acid. Sulfur dioxide in the atmosphere, released by volcanic activity, reacts with water vapor in the presence of ultraviolet light to produce sulfuric acid. The acid condenses into droplets that form thick cloud layers between 45 and 70 kilometers altitude. Sulfuric acid is highly corrosive. It can destroy organic materials, dissolve metals, and cause severe chemical burns. On Earth, battery acid is dilute sulfuric acid. Venus's clouds are more concentrated. The droplets have an acid concentration of about 75–85%, compared to the 30–50% concentration in typical car batteries. Any spacecraft or instrument passing through these clouds must be designed to resist chemical attack. The cloud deck is incredibly thick and opaque. It completely shrouds the planet, preventing any visual observation of the surface from space. The clouds reflect about 70% of the sunlight that reaches Venus, contributing to the planet's brilliant appearance in our sky. Only about 10% of solar energy penetrates to the surface. Despite being closer to the sun, Venus's surface receives less sunlight than Earth's because of this extreme cloud cover. The surface is dimly lit, comparable to a heavily overcast day on Earth, with illumination levels around 14,000 lux. Within the clouds, conditions are dynamic. Lightning may occur, though observations have been controversial, and the detection of lightning on Venus remains debated. The clouds also contain mysterious ultraviolet absorbing particles that create dark, irregular patterns when Venus is viewed in UV wavelengths. These patterns change over time, moving with the winds. Scientists are unsure what these absorbers are. Proposed explanations include iron chloride, sulfur compounds, or even hypothetical microorganisms adapted to live in the clouds, though the last possibility is considered highly speculative. The atmospheric circulation on Venus is bizarre and poorly understood. Despite the planet's incredibly slow rotation, the upper atmosphere races around Venus in only 4 Earth days. This phenomenon, called superrotation, means the atmosphere circles the planet about 60 times faster than the surface rotates. Wind speeds at the cloud tops reach 350 kilometers per hour, among the fastest winds in the solar system. Yet at the surface, winds are sluggish, typically moving at only 1 to 3 kilometers per hour. This differential wind speed, with the atmosphere moving much faster than the solid planet, has puzzled scientists for decades. On Earth, our atmospheric circulation is powered by solar heating and organized by our planet's rotation through the Coriolis effect. Venus rotates too slowly for the Coriolis effect to be significant. The mechanism driving superrotation must be different. Current theories involve atmospheric tides raised by solar heating and complex wave interactions in the atmosphere, but the details remain uncertain. The atmosphere circulates in a pattern called Hadley cells. Warm air rises at the equator, flows toward the poles at high altitude, sinks as it cools at the poles, then flows back toward the equator at lower altitude. On Earth, the Coriolis effect breaks this simple pattern into multiple circulation cells in each hemisphere. On slowly rotating Venus, the circulation is simpler but more extreme. The single cell in each hemisphere transports heat efficiently from equator to poles, contributing to the uniform surface temperature. Above the clouds, the atmosphere becomes progressively thinner. The temperature increases with altitude in this region, reaching a maximum of about 300 degrees Kelvin at around 120 kilometers altitude in the thermosphere. Then it drops again at higher altitudes, falling to 100 degrees Kelvin or less in the mesosphere. This temperature inversion, warm above and cool below, is the opposite of what might be expected and results from absorption of solar ultraviolet radiation by CO2. The atmospheric structure of Venus can be divided into distinct layers, each with its own characteristics. The troposphere extends from the surface to about 65 kilometers altitude. This is where most of the atmospheric mass resides and where temperature decreases steadily with altitude. The pressure drops from 93 bars at the surface to about 0.1 bars at 65 kilometers. The temperature falls from 464 degrees Celsius to about minus 10 degrees Celsius. This is an enormous temperature gradient, far steeper than anything experienced on Earth. Within the troposphere, convection occurs. Though it's sluggish compared to Earth's atmosphere, hot air rises from the scorching surface, cools as it expands at lower pressures, then eventually descends again. This convective overturning helps transport heat from the surface upward, though the thick atmosphere means the timescale for complete overturning is measured in years rather than days or weeks as on Earth. The mesosphere extends from about 65 to 95 kilometers. Here, temperatures reach their coldest, dropping to around 100 Kelvin or minus 173 degrees Celsius at about 100 kilometers altitude. This cold mesopause region is where hazes form above the main cloud deck. The hazes consist of fine particles, possibly sulfuric acid aerosols, or photochemically produced sulfur compounds. The exact composition remains uncertain because spacecraft have not sampled this region directly with sufficient instrumentation. The thermosphere, from roughly 95 to 200 kilometers, is where solar ultraviolet radiation heats the upper atmosphere. Temperatures rise dramatically with altitude, as UV photons break apart CO2 molecules, and the freed atoms absorb energy. At 120 kilometers, daytime temperatures can reach 300 Kelvin, warm despite the low density. The thermosphere is also where chemical reactions driven by solar UV create exotic molecules not found at lower altitudes. The exosphere is the outermost layer, where the atmosphere gradually fades into space. Individual atoms and molecules move on ballistic trajectories, occasionally escaping to space if they achieve sufficient velocity. Hydrogen, being the lightest element, escapes most readily. Heavier atoms like oxygen and nitrogen escape much more slowly. The exosphere is where Venus interacts directly with the solar wind, the stream of charged particles flowing from the sun. The interaction between Venus's atmosphere and the solar wind creates a bow shock, a boundary where the solar wind slows abruptly as it encounters the obstacle of Venus's atmosphere and induced magnetic field. The bow shock sits about 2,000 kilometers above the surface on the day side, closer on the night side. Behind the bow shock, the solar wind plasma flows around Venus, creating a magnetotail extending millions of kilometers downwind. This magnetotail is where atmospheric ions are stripped away and lost to space. Understanding the vertical structure of Venus's atmosphere helps us understand how energy flows through the system. Solar energy enters primarily at the cloud tops and in the upper atmosphere, where UV radiation is absorbed. Some energy penetrates to the surface as diffuse, visible light. Energy leaves the planet primarily as infrared, radiation from the upper atmosphere and cloud tops. The balance between incoming and outgoing energy determines Venus's equilibrium temperature. The massive greenhouse effect means the equilibrium is achieved only when the surface and lower atmosphere are extraordinarily hot, hot enough that sufficient infrared radiation can escape from the upper atmosphere to balance the incoming solar energy. The chemical composition of Venus's atmosphere also varies with altitude. At the surface, CO2 and nitrogen dominate, with small amounts of sulfur dioxide, carbon monoxide, and other gases. Water vapor is present at concentrations of only a few tens of parts per million, essentially trace amounts. As you ascend, the composition remains similar until you reach the cloud layers, where sulfuric acid aerosols become a major constituent. Above the clouds, photochemical reactions driven by UV light create additional species: atomic oxygen, carbon monoxide, sulfur monoxide, and others. These reactive species recombine and form more complex molecules, creating a rich photochemistry that varies between day and night sides. One intriguing aspect is the presence of carbon monoxide. On Earth, CO is rare because oxygen rapidly oxidizes it to CO2. On Venus, with essentially no free oxygen in the lower atmosphere, CO persists at concentrations of about 20 to 40 parts per million. The CO is produced by photodissociation of CO2 in the upper atmosphere. Sunlight breaks apart CO2 molecules, freeing oxygen atoms that escape or recombine, while the carbon monoxide descends to lower altitudes. Eventually, CO is recycled back to CO2, but the rate of this process is slow enough that measurable CO accumulates. Sulfur compounds are particularly important in Venus's atmosphere. Sulfur dioxide exists at concentrations of about 150 parts per million near the surface, but the concentration drops dramatically at higher altitudes. The SO2 is consumed in reactions that produce sulfuric acid clouds. In the upper atmosphere, UV light breaks down SO2 and H2O, initiating a chain of reactions that ultimately produces H2SO4, sulfuric acid. The acid condenses into droplets that form the main cloud layers. The sulfur cycle is complex and not fully understood. Where does the sulfur come from? Volcanic eruptions are the primary source, but we don't know if the current volcanic outgassing rate is sufficient to maintain the observed SO2 levels, or if there are other sources or reservoirs of sulfur in Venus's environment. Trace gases in Venus's atmosphere provide clues about geological and potentially biological processes. Phosphine, if it truly exists, as claimed in the controversial 2020 detection, would be particularly interesting because it's difficult to produce abiotically. The molecule is unstable and should be rapidly destroyed by photochemistry and reactions with sulfuric acid. If phosphine is present at detectable levels, there must be a continuous source. Proposed abiotic sources include volcanic activity, lightning-driven chemistry, or unusual reactions in the sulfuric acid clouds. Alternatively, if biological processes could produce phosphine on Venus as they do on Earth, that would be extraordinary. However, subsequent analyses have failed to confirm the phosphine detection, and the debate continues. Other trace gases of interest include carbonyl sulfide, OCS, a molecule containing carbon, oxygen, and sulfur. OCS is stable and can provide information about sulfur cycling and possible volcanic activity. Measurements of OCS and its variations over time could reveal changes in volcanic outgassing rates. Noble gases like argon, neon, and xenon are particularly valuable for understanding planetary evolution. These inert gases are not produced or consumed by chemical reactions, so their abundances reflect the planet's formation conditions and subsequent loss processes. The argon-40 to argon-36 ratio, for example, provides information about how much of Venus's interior has outgassed over time, which constrains models of volcanic history and mantle convection. The atmospheric chemistry of Venus is further complicated by its day-night asymmetry. On the day side, solar UV drives vigorous photochemistry, breaking molecules apart and creating reactive radicals. On the night side, these reactions slow or stop, allowing different equilibria to establish. The slow rotation means the night side spins nearly 2 Earth months in darkness, ample time for chemical differences to develop. Spacecraft observations have detected compositional differences between day and night sides, particularly in the upper atmosphere where photochemistry is most important. Understanding Venus's atmospheric composition and structure is essential for understanding the planet's climate and evolution. Every molecule tells part of the story: where Venus came from, what processes have operated over its history, and how the planet functions today. Future missions will measure atmospheric composition with unprecedented precision, resolving isotopic ratios, detecting trace gases at parts per billion levels, and monitoring how composition varies with location and time. These measurements will revolutionize our understanding of Venus's atmosphere and its role in the planet's evolution. The very topmost layer of the atmosphere streams away into space, blown by the solar wind. Venus has a long ion tail, similar to a comet's tail, extending millions of kilometers downwind from the Sun. The solar wind particles interact with Venus's upper atmosphere, ionizing atoms and stripping them away. This process has operated for billions of years, gradually eroding the atmosphere. Heavier gases like CO2 and nitrogen resist this erosion, but lighter elements, especially hydrogen, escape readily. The loss of hydrogen is critical to understanding Venus's climate history, as we'll soon explore. Atmospheric composition measurements reveal important clues about Venus's past. The deuterium to hydrogen ratio in Venus's atmosphere is about 150 times higher than Earth's ratio. Deuterium is heavy hydrogen, an isotope with one proton and one neutron in its nucleus, instead of just one proton. Because deuterium is twice as heavy as normal hydrogen, it escapes to space much more slowly. Over billions of years, as normal hydrogen escaped preferentially, the remaining hydrogen in Venus's atmosphere became progressively enriched in deuterium. The extreme deuterium enrichment observed today suggests that Venus once had far more hydrogen than it does now. Since hydrogen is a component of water, this implies Venus once had substantial water, possibly even oceans, the runaway greenhouse. The greenhouse effect on Venus represents the most extreme example of this phenomenon anywhere in the solar system. To understand what happened to Venus, we need to understand how greenhouse warming works and why it ran out of control on this planet while remaining stable on Earth. The basic mechanism of the greenhouse effect is straightforward. Sunlight, which includes visible light and ultraviolet radiation, passes relatively easily through atmospheric gases and reaches the planet's surface. The surface absorbs this energy and warms up. Like any warm object, the surface radiates energy back into space, but the surface is much cooler than the sun, so it radiates primarily in the infrared part of the spectrum, heat radiation invisible to our eyes. Here's where greenhouse gases matter. Gases like carbon dioxide, water vapor, and methane are largely transparent to visible light, but strongly absorb infrared radiation. When infrared radiation from the surface tries to escape to space, greenhouse gases absorb it, warming the atmosphere. The atmosphere then re-radiates some of this energy back toward the surface and some outward to space. The result is that the surface warms beyond what it would be if the atmosphere were transparent to infrared. The more greenhouse gas present and the higher the pressure, the stronger this effect becomes. On Earth, the greenhouse effect is beneficial and necessary for life as we know it. Without any greenhouse gases, Earth's average surface temperature would be about minus 18 degrees Celsius, well below the freezing point of water. Instead, with our current atmospheric composition, the average temperature is a comfortable plus 15 degrees Celsius. The 33-degree difference is due almost entirely to greenhouse warming, with water vapor and CO2 being the primary contributors. Venus takes this process to an extreme. With an atmosphere nearly pure CO2 at a crushing 93 bars of pressure, infrared radiation from the surface can barely escape. The greenhouse effect raises the surface temperature by more than 500 degrees Celsius compared to what it would be without an atmosphere. This temperature is determined by energy balance. The planet must radiate as much energy to space as it receives from the sun, with greenhouse gases blocking most surface infrared emission. Only when the lower atmosphere becomes extremely hot can enough radiation escape from the upper atmosphere to balance incoming solar energy. The term runaway greenhouse effect describes a positive feedback process. Positive feedbacks amplify changes. On Venus, this worked as follows. The planet begins with some water and some CO2. Solar heating causes water to evaporate. Water vapor is an excellent greenhouse gas. even better than CO2 at trapping heat per molecule. As more water evaporates into the atmosphere, the greenhouse effect strengthens, raising temperatures further. This causes even more water to evaporate, which strengthens the greenhouse effect more in a self-reinforcing cycle. At moderate temperatures, liquid oceans provide a buffer. Most of Earth's water is in liquid form in the oceans, with only a tiny fraction as atmospheric vapor at any given time. The oceans represent an enormous reservoir that resists rapid changes. But on Venus, as temperatures climbed, the buffer failed. If surface temperatures reach the boiling point of water, the liquid phase can no longer exist. The entire ocean evaporates into the atmosphere. At this point, the greenhouse effect from water vapor becomes overwhelming. With the ocean in vapor form, a steam atmosphere develops. This is thought to have been Venus's condition a few 100 million years after its formation. Solar ultraviolet radiation penetrating to the upper atmosphere photodissociates water molecules, breaking H2O into hydrogen and oxygen. Hydrogen, being the lightest element, escapes to space. Oxygen, being more reactive, combines with other materials. Some oxidizes surface rocks, some combines with volcanic gases, and some remains in the atmosphere. As hydrogen escapes, the planet loses water irreversibly. There's no mechanism to replace it. Over hundreds of millions or billions of years, the steam atmosphere dried out, leaving only trace amounts of water, vapor. The high deuterium to hydrogen ratio in today's Venusian atmosphere is the signature of this ancient hydrogen escape. It's as if Venus's atmosphere remembers the vanished ocean through the isotopic fingerprint left behind. Meanwhile, volcanic activity continued to pump CO2 into the atmosphere. On Earth, CO2 is removed from the atmosphere through several mechanisms. The most important is the weathering of silicate rocks in the presence of water. Rainfall, slightly acidic because CO2 dissolves in water-forming carbonic acid, reacts with minerals in exposed rock. These weathering reactions consume CO2, converting it into bicarbonate ions that wash into the oceans. Marine organisms use these ions to build shells and skeletons from calcium carbonate. When these organisms die, their remains settle to the sea floor, eventually forming limestone and other carbonate rocks. Through this process, enormous amounts of CO2 become locked in Earth's crust. This weathering carbonate cycle acts as a thermostat for Earth's climate. If the planet warms, more water evaporates, rainfall increases, weathering accelerates, more CO2 gets removed from the atmosphere, and the greenhouse effect weakens, cooling the planet back down. If the planet cools, ice forms, rainfall decreases, weathering slows, volcanic CO2 accumulates in the atmosphere, the greenhouse effect strengthens, and temperatures rise. This negative feedback has kept Earth's climate relatively stable for billions of years. On Venus, once the water was gone, this thermostat broke. Without liquid water, silicate weathering couldn't proceed. Volcanic CO2 accumulated in the atmosphere with no removal mechanism. Over geological time, Venus outgassed most of its internal CO2, building up the thick atmosphere we observe today. Earth has just as much CO2 as Venus, but ours is locked in carbonate rocks in the crust, not in the atmosphere. The presence or absence of liquid water made all the difference. The question scientists debate is whether Venus ever had an extended habitable period with liquid water oceans, or whether it went straight into a runaway greenhouse shortly after formation. This question matters enormously for understanding Venus's history, and for assessing the habitability of exoplanets. Recent climate modeling suggests Venus might have maintained habitable conditions for up to 2 billion years after its formation. These simulations assume Venus started with an Earth-like atmosphere and oceans. The key factor enabling long-term habitability in these models is cloud cover. On a planet with oceans and water vapor in the atmosphere, clouds form. Clouds reflect sunlight back to space, increasing the planet's albedo. With sufficient cloud cover, especially on the day side of a slowly rotating planet, Venus could have remained cool enough for liquid water to persist on the surface, despite receiving more solar energy than Earth. In these optimistic scenarios, Venus would have had temperate surface temperatures, possibly 20 to 40 degrees Celsius on average. Continental landmasses might have existed, with oceans covering the lowlands. The slow rotation would create long days and nights, but thick daytime clouds could prevent excessive heating. Life might conceivably have emerged on such a world. The planet could have remained habitable for a significant fraction of solar system history, comparable to the time life has existed on Earth. Other researchers are more skeptical. An alternative scenario proposes that Venus never cooled enough for liquid water to condense. In this view, Venus had a magma ocean that persisted for perhaps 100 million years after formation, fed by the high-energy impacts of the late stages of planetary accretion and by the decay of short-lived radioactive isotopes. The atmosphere during this period would have been a hot steam atmosphere. The magma ocean would have slowly solidified, but before it could fully solidify and cool, the runaway greenhouse locked in. In this scenario, liquid water never existed on the surface. Any water delivered to Venus remained as vapor, eventually photodissociated and lost to space. Evidence supporting the dry Venus scenario includes atmospheric composition measurements. The extreme dryness of Venus's interior, inferred from the composition of volcanic gases, suggests the mantle never hydrated. If oceans existed, water should have been absorbed into minerals in the crust and mantle through hydrothermal activity and subduction, as happens on Earth. The absence of significant water in Venus's interior suggests oceans never existed long enough for this process to operate. A 2024 study analyzing Venus's atmospheric chemistry concluded that volcanic gases on Venus contain at most 6% water vapor compared to the steam-dominated eruptions on Earth. This dry volcanism indicates a dry interior, consistent with Venus never having had long-lived surface water. The researchers argue that the lack of water implies Venus's surface has been inhospitable for most or all of its history. The debate remains unresolved. We need more data, particularly detailed surface geology and geochemistry measurements, to determine whether Venus once had oceans. The presence of certain minerals, like granite or clay minerals, would indicate water-rock interactions that could only occur with liquid water. Future missions will search for these signatures. Regardless of when the runaway greenhouse occurred, its consequences are clear. Once initiated, the process was irreversible. Venus transformed from whatever it was into the Inferno we observe today. The surface became hot enough to glow faintly in the dark, radiating dull red heat like the inside of an oven. The thick CO2 atmosphere trapped this heat, maintaining the extreme temperature. Any remaining water was lost to space, eliminating any possibility of returning to a temperate state. The implications for Earth are sobering. Our planet has been fortunate. We formed at just the right distance from the sun where liquid water could remain stable. Our tectonics and weathering cycles have kept atmospheric CO2 in check, but these systems are delicately balanced. If Earth's temperature rose enough to evaporate a significant fraction of the oceans, we could potentially trigger a runaway greenhouse similar to Venus's. This is thought to be nearly impossible under current or projected future conditions because Earth receives less solar energy than Venus, and our Sun's output increases very slowly over hundreds of millions of years. However, the Venusian example demonstrates that planetary climates can undergo catastrophic transitions from which there is no return. Understanding the runaway greenhouse on Venus helps us understand the inner edge of the habitable zone around stars. The habitable zone is the range of distances where a planet can maintain liquid water on its surface, too close to the star and runaway greenhouse. Conditions develop too far, and the planet freezes. Venus sits just inside the inner edge of our Sun's habitable zone, demonstrating where that boundary lies. This knowledge is crucial for assessing potentially habitable exoplanets. Planets similar to Venus, receiving similar amounts of stellar energy, are unlikely to be habitable, even if they have Earth-like sizes and masses when Venus had water. The story of Venus's lost oceans is one of the most compelling mysteries in planetary science. Did Venus once have conditions similar to early Earth, with liquid water oceans covering portions of its surface? If so, how long did these oceans last, and what caused them to disappear? The answers fundamentally alter our understanding of planetary evolution and the potential for life beyond Earth. Multiple lines of evidence suggest Venus once possessed substantial quantities of water. The most telling evidence comes from measurements of hydrogen isotopes in Venus's current atmosphere. As discussed earlier, the deuterium to hydrogen ratio on Venus is enriched by a factor of about 150 compared to Earth. This extreme enrichment implies that Venus started with far more hydrogen than it has today. Since hydrogen is lost preferentially to space due to its low atomic mass, the remaining hydrogen has become progressively enriched in the heavier deuterium isotope over billions of years. Working backward from the current ratio, scientists can estimate how much water Venus originally possessed. Different studies arrive at somewhat different numbers depending on the assumptions made, but most estimates suggest Venus started with enough water to cover the planet in a global ocean, tens to hundreds of meters deep. This is far less than Earth's oceans, which, if spread evenly across Earth's surface, would be about 2.7 kilometers deep. But it's substantial enough that, given the right conditions, liquid water could have existed as oceans, lakes, or seas on Venus's surface. The timing of water loss is crucial. If Venus lost its water quickly, within the first few 100 million years of its existence, then the planet would have been inhospitable for almost its entire history. If water persisted for 1 billion years or more, then Venus could have experienced an extended habitable epoch, possibly long enough for life to emerge. Climate models suggest a range of possibilities. Optimistic models, published by researchers at NASA's Goddard Institute for Space Studies and other institutions, indicate that Venus could have maintained temperate surface conditions for up to 2 billion years. These models assume Venus formed with an Earth-like atmosphere and began with a shallow ocean. The slow rotation of Venus, the same 243-day period it has today, plays a surprisingly positive role in these scenarios. On a slowly rotating planet with an atmosphere and oceans, clouds tend to form preferentially on the day side. The long days mean the sun beats down continuously for weeks, causing intense evaporation. But this evaporation produces thick cloud cover that reflects sunlight back to space. In the models, Venus could have maintained a cloud shield that kept the surface cool despite receiving more solar energy than Earth. Surface temperatures might have been in the range of 20 to 40 degrees Celsius, comfortably within the range for liquid water. The topography of Venus, as mapped by radar, provides some support for this scenario. Using data from NASA's Magellan mission, which mapped 98% of Venus's surface in the 1990s, scientists created simulations where the low-lying regions were filled with water while highland areas remained as dry land. The hypothetical Venusian continents would have been concentrated in two main areas: Ishtar Terra in the northern hemisphere and Aphrodite Terra in the equatorial region. These highlands, particularly the tesserae terrain, show complex deformation patterns that might require the presence of water to explain fully, though this interpretation is debated. If Venus did have oceans, they were likely shallower and less extensive than Earth's oceans. Computer models suggest that having more land area, especially in the tropics, would have helped stabilize Venus's climate by limiting evaporation. With less water vapor in the atmosphere, the water vapor greenhouse effect would be weaker, helping keep temperatures down. It's a delicate balance, and one that might have been sustainable for a considerable period. What ended this habitable period, if it existed? The primary driver was likely the gradual brightening of the sun. Stars like our sun slowly increase in luminosity over time, as hydrogen fusion in the core changes the core's composition. When the solar system formed 4.6 billion years ago, the sun was about 30% dimmer than it is today. Over billions of years, as the sun brightened, Venus received more and more solar energy. At some point, the increasing solar flux overwhelmed the cooling mechanisms, and the runaway greenhouse began. Different studies place the end of habitability at different times. A 2023 study suggested that if Venus ever had oceans, they must have disappeared more than 3 billion years ago. This estimate comes from analyzing oxygen loss and the degassing of radiogenic argon, a noble gas produced by radioactive decay within the planet. The atmospheric abundance of argon-40 provides constraints on how much of Venus's interior has degassed over time, which in turn constrains how much water could have been present and when it was lost. Another research team, using different modeling approaches, concluded in 2021 that Venus might never have had surface water at all. Their simulations of the young solar system showed that even with the fainter young sun, Venus's initial formation conditions were too hot. The planet likely emerged from its formation with a thick steam atmosphere from the heat of accretion and late-stage giant impacts. This steam atmosphere never cooled, enough for water to condense as rain or oceans. Instead, the water remained as vapor, was photodissociated by solar ultraviolet radiation, and the hydrogen escaped to space. In this view, Venus was born hot and has remained inhospitable ever since. The debate hinges on uncertainties in how planets form and cool. The late stages of planetary accretion involve massive impacts as planetary embryos collide and merge. These impacts release enormous amounts of energy, melting or partially melting the growing planet. The resulting magma ocean must cool and solidify before liquid water can exist on the surface. How long this cooling takes depends on the planet's size, the thickness of its atmosphere, and the frequency of late impacts. For Earth, cooling took perhaps 10 to 100 million years. For Venus being closer to the Sun and receiving more solar energy, cooling might have taken longer or might never have reached the point where surface temperatures dropped below water's boiling point. One hypothesis suggests that Venus's climate could have undergone a sudden transition from habitable to hellish due to a triggering event. Massive volcanic eruptions could have injected enormous quantities of CO2 and water vapor into the atmosphere, tipping the balance and initiating the runaway greenhouse. Evidence for such catastrophic volcanism exists on Venus's surface, which we'll explore in detail later. If Venus had stable oceans for 1 billion years or more, then a sudden outburst of volcanic activity could have ended the habitable period relatively quickly, geologically speaking, perhaps over just a few million years. The loss process itself would have been gradual on human timescales, but rapid in geological terms. As temperatures rose, evaporation increased. More water vapor in the atmosphere strengthened the greenhouse effect, raising temperatures further. The ocean level fell as water moved into the atmosphere. Eventually, the entire ocean evaporated. At that point, with a thick steam atmosphere, Venus entered a moist greenhouse state. In the upper atmosphere, solar UV radiation broke apart water molecules. Hydrogen, being light, achieved escape velocity and was lost to space at a rate of millions to billions of tons per year. Oxygen left behind reacted with surface rocks and atmospheric gases. Over hundreds of millions of years, the steam atmosphere dried out, leaving Venus as we see it today. If Venus did have habitable conditions for an extended period, could life have emerged? The origin of life on Earth is thought to have occurred within a few 100 million years of our planet becoming habitable. The earliest evidence of life on Earth dates to about 3.8 billion years ago, possibly earlier. If Venus remained habitable for 1 to 2 billion years, that would have provided ample time for life to arise and evolve. Any Venusian life would have faced increasing stress as temperatures rose and the ocean shrank. Could life have adapted? On Earth, life exists in extreme environments, in hot springs, at temperatures approaching the boiling point, in acidic lakes, in the dry valleys of Antarctica. Thermophils and acidophiles demonstrate that life can adapt to harsh conditions, but there are limits. No known life survives in environments as extreme as Venus's surface today. If life existed on ancient Venus, it would have been extinguished when conditions became too severe, probably long before the oceans completely evaporated. One speculative possibility is that life could have retreated to the clouds as surface conditions deteriorated. The cloud layer at 50 to 60 kilometers altitude has temperatures and pressures that are Earth-like, as mentioned earlier. If microorganisms could adapt to survive in sulfuric acid droplets, they might persist in the clouds even after the surface became uninhabitable. This idea, proposed decades ago and periodically revived, remains highly speculative. No evidence supports the existence of life in Venus's clouds, though it's also true that we haven't looked very hard yet. The detection of phosphine gas in Venus's atmosphere in 2020 sparked intense interest and controversy. Phosphine, a molecule of 1 phosphorus and 3 hydrogen atoms, is produced on Earth primarily by biological processes, though some non-biological production also occurs. The original study claimed to detect phosphine at concentrations of about 20 parts per billion in Venus's clouds. If confirmed, this would be difficult to explain through known abiotic chemistry, possibly suggesting biological activity. However, subsequent analyses question the detection. Some researchers reanalyzed the data and argued the signal was actually sulfur dioxide, not phosphine. Others suggested that if phosphine is present, it could be produced by volcanic activity or unusual atmospheric chemistry involving the sulfuric acid clouds. As of now, the phosphine detection remains disputed, with no consensus on whether the molecule is actually present in detectable amounts. Even if present, its origin could be non-biological. The phosphine claim illustrates both the excitement and the challenges of searching for life beyond Earth. Future missions to Venus will search for clues about the planet's watery past. The Da Vinci mission, scheduled to launch in the early 2030s, will descend through Venus's atmosphere and take high-resolution images of the surface, particularly of the Tesserae highlands. These ancient terrains might preserve geological features formed in the presence of water. Veritas will use radar to map surface composition and look for minerals that form only in the presence of water. If granite-like rocks exist on Venus, that would indicate water was present during their formation. The absence of such rocks would support the dry Venus hypothesis. Understanding Venus's history matters beyond curiosity about our neighboring planet. It informs our understanding of planetary habitability and the inner edge of habitable zones around other stars. Many exoplanets discovered by telescopes orbit closer to their stars than Earth orbits the Sun, receiving more stellar energy. Are these planets hellish worlds like Venus, or could some maintain stable climates despite higher stellar flux? Venus provides the crucial example in our own solar system. It's a cautionary tale of how a planet can transform from potentially habitable to utterly hostile, a transformation that appears to be permanent. A world of volcanoes. When the Magellan spacecraft arrived at Venus in 1990, it carried a synthetic aperture radar capable of imaging the surface through the planet's thick clouds. Over 4 years, Magellan mapped 98% of Venus's surface with radar, revealing a world profoundly shaped by volcanic activity. The images stunned planetary scientists. Venus is one of the most volcanic bodies in the solar system, rivaling Jupiter's moon Io in the intensity and variety of its volcanism. About 85% of Venus's surface is covered by volcanic plains, vast expanses of solidified basaltic lava flows. These plains are relatively flat, with gentle slopes and low relief. They represent episodes of extensive effusive volcanism, where low viscosity lava erupted and flowed across the surface, building up layer upon layer of basalt. The plains resemble the Maria on Earth's moon or the flood basalt provinces on Earth, but they're far more extensive. On Earth, the largest flood basalt provinces cover a few million square kilometers. On Venus, volcanic plains cover hundreds of millions of square kilometers, nearly the entire planet. Superimposed on these plains are volcanic constructs of many types. Venus has more than 100,000 volcanic features, a staggering number that dwarfs Earth's volcanoes. Many are small shield volcanoes, gently sloped cones built by repeated eruptions of fluid basaltic lava. The largest volcanoes on Venus are truly massive. Mont Mons, the tallest volcano and the highest point on Venus, rises 8 kilometers above the mean planetary radius. Ozymandias and Sapasmands are also huge shield volcanoes, each several hundred kilometers across at the base and rising several kilometers high. These giant shield volcanoes resemble Hawaii's volcanoes, or Olympus Mons on Mars. They form above mantle hotspots where plumes of hot rock rise from deep in the mantle, melting as they reach lower pressures near the surface. The resulting magma erupts repeatedly from a central vent, building the volcanic edifice over millions of years. On Earth, tectonic plate motion carries volcanoes away from their hotspots, creating volcanic island chains like Hawaii. On Venus, without plate tectonics, volcanoes remain stationary above their hotspots, growing larger and larger as eruptions continue. Venus also exhibits volcanic features not found on any other planet. Pancake domes are one such oddity. These are large, flat-topped, steep-sided domes, typically 25 to 50 kilometers in diameter and about 1 kilometer high. They look remarkably like pancakes, hence the name. Pancake domes are thought to form from the eruption of highly viscous, silica-rich lava, more like Earth's rhyolite or dacite volcanoes than typical basaltic volcanism. The thick lava oozes out and piles up around the vent, unable to flow far because of its high viscosity, creating the distinctive pancake shape. Some pancake domes have fractures on their tops, suggesting the surface solidified while the interior remained molten and continued to inflate. Coronae are another unique Venusian feature. These are large, roughly circular structures ranging from 100 to over 1,000 kilometers in diameter. They consist of concentric rings of ridges and troughs, often with volcanic features in the center. About 500 coronae have been identified on Venus. They're thought to form above mantle plumes. As a plume rises, it domes the surface upward. Volcanic eruptions occur at the center. As the plume wanes, the domed region subsides, creating the concentric fracture patterns. The result is a complex structure showing both uplift and subsidence, volcanism and tectonism, all in one feature. Arachnoids, so named because they resemble spiderwebs, are related to corona, but smaller and more numerous. They have a central volcanic edifice surrounded by radial fractures that extend outward like spider legs. About 250 arachnoids are known. Their origin is thought to be similar to coronae, resulting from smaller upwelling plumes. Tesserae are the oldest and most geologically complex terrains on Venus. The name comes from the Greek word for mosaic tiles, referring to the blocky appearance of these regions in radar images. Tesserae cover about 8% of the surface and are characterized by intensely deformed terrain with multiple sets of intersecting ridges and grooves. The deformation suggests these regions experience compression, extension, and possibly shearing, indicating complex tectonic forces. Tesserae form the highland regions, most notably in Ishtar Terra and Aphrodite Terra. These highlands may represent ancient crust, possibly continents, formed early in Venus's history, when tectonic processes were more active, or when water was present. One striking aspect of Venus's surface is the relative lack of impact craters. The planet has only about 900 craters larger than 2 kilometers in diameter. For comparison, the Moon has hundreds of thousands of craters. Mercury is saturated with craters. Even Earth, despite active erosion and plate tectonics that erase craters over time, has preserved about 190 confirmed impact structures. Venus's low crater count indicates a young surface. The impact craters that do exist on Venus show some interesting characteristics. Many are remarkably pristine, with sharp rims and well-preserved ejecta blankets. This indicates that erosion on Venus, despite the high temperatures, is extremely slow. without wind-driven sand, water erosion, or ice. The ICISOR main erosive process is chemical weathering of rocks by the hot, dense atmosphere. This process operates over millions of years, far too slowly to modify craters significantly on timescales of hundreds of millions of years. Venusian craters also show some unique features related to the thick atmosphere. Small impactors, those less than a few hundred meters across, don't reach the surface intact. They break up and vaporize during entry through the dense atmosphere. This filtering effect means Venus has few small craters. On airless bodies like the Moon, craters range from microscopic pits to giant basins thousands of kilometers across. On Venus, there's a cutoff at about 2 to 3 kilometers diameter. Anything smaller gets filtered out by atmospheric entry effects. Some craters on Venus are surrounded by dark, parabolic features extending downwind for hundreds of kilometers. These are radar dark because they're smoother than surrounding terrain. They're thought to form when the impactor breaks up during atmospheric entry, producing a shower of fragments that strike the surface in an elongated pattern. The fragments and the impact-generated ejecta are then transported downwind by winds near the surface, creating the parabolic patterns. These features provide information about wind directions at the surface at the time the craters formed. Crater counting is the primary method for determining surface age on planets without samples to date radiometrically. Impact craters accumulate over time as asteroids and comets strike the surface. The older a surface, the more craters it should have, assuming a constant impact rate. From the number and size distribution of craters on Venus, scientists estimate the average surface age is between 150 million and 1 billion years. This is young compared to the 4.5 billion year age of the solar system. Something reset Venus's surface relatively recently in geological terms. The distribution of craters on Venus is statistically random, unlike Mars or the Moon, where different regions show vastly different crater densities indicating different ages. Venus's craters appear uniformly distributed across the surface. This uniform distribution suggests that whatever resurfaced Venus affected the entire planet or most of it. Regional variations in crater density are small and within statistical uncertainty. A small percentage of Venus's craters show evidence of modification after formation. Some craters are partially filled with lava flows from nearby volcanic features. Others show tectonic deformation, with fractures cutting through the crater or the crater rim being deformed by regional compression or extension, but the fraction of modified craters is small, suggesting that volcanic and tectonic activity has been relatively limited since most craters formed. This observation supports the catastrophic resurfacing hypothesis, where a global volcanic event reset the surface 300 to 500 million years ago, after which activity declined. Beyond the craters and major volcanic features, Venus's surface includes many other interesting landforms. Ridge belts are linear to curvilinear structures, tens to hundreds of kilometers wide and thousands of kilometers long, consisting of closely spaced parallel ridges. They're thought to form from compression of the lithosphere, similar to fold belts on Earth, but on a more extensive scale. Two major ridge belt systems exist, one near the South Pole and one near the North Pole. Their origin is unclear, but might relate to large-scale mantle convection patterns or to global contraction as the planet cooled. Rift zones are also present, regions where the lithosphere is being pulled apart. The most prominent rift systems are associated with the volcanic rises of Beta Regio and Atla Regio. These rifts feature parallel grabens, linear troughs formed by normal faulting as the crust extends. Some rifts show evidence of recent volcanic activity, with fresh lava flows filling the graben floors. The rifts may represent failed attempts at plate boundary formation, places where extension began but never developed into a full spreading center. Novae are another unique Venusian feature. These are radial systems of fractures and ridges, typically 100 to 200 kilometers across, with patterns resembling a starburst or nova. About 60 novae have been identified. They're thought to form above mantle plumes, possibly as precursors to coronae. The radial pattern develops as rising magma domes the surface and induces radial stress patterns in the overlying lithosphere. Some novae show central volcanic edifices, while others are purely tectonic. Chasmata are large, deep rift or canyons. The largest, Diana Chasma in Aphrodite Terra, is over 280 kilometers wide and extends for thousands of kilometers. Chasmata form by lithospheric extension, where the crust is pulled apart and subsides along normal faults. The floors of some chasmata are filled with lava flows, hun, indicating volcanic activity accompanied the tectonic extension. These features demonstrate that Venus has experienced significant tectonic stresses, though not organized into a plate tectonic system. The Tesserae highlands are particularly intriguing. These regions cover about 8% of the surface and are the most heavily deformed terrains on Venus. The word tessera comes from ancient Greek, referring to the small tiles used in mosaics. In radar images, tesserae appear as complex mosaics of intersecting ridges and grooves, indicating multiple episodes of deformation. Some areas show 2 or 3 sets of intersecting structures at different orientations, suggesting the terrain experienced compression from different directions at different times. The deformation mechanisms that created tesserae are debated. Some researchers propose that tesserae formed through intense compression and shortening, perhaps analogous to Earth's mountain belts. Others suggest a combination of compression, extension, and possibly strike-slip faulting. The complex deformation could indicate that tesserae are very old, predating the current stagnant lid regime, and formed when Venus's tectonic activity was more intense or organized differently. One hypothesis is that tesserae are the remnants of ancient continents, analogous to Earth's continental crust. On Earth, continents form through complex processes involving water, plate tectonics, and magma chemistry. Continental crust is enriched in silica and other incompatible elements, making it less dense than oceanic crust. If Venus once had continents formed in the presence of water, they might now be represented by the Tesserae highlands. Testing this hypothesis requires determining the composition of Tesserae rocks. Are they basaltic like most of Venus, or are they more silica-rich, like Earth's granitic continental crust? Future missions carrying spectrometers will seek to answer this question. Maxwell Montes, the highest mountain range on Venus, lies within Ishtar Terra, one of the major highland regions. The mountains rise about 11 kilometers above the mean planetary radius, higher than Mount Everest rises above sea level on Earth. The range formed through compressional tectonics, where the crust was squeezed and thrust upward. The western edge of Maxwell Montes drops off dramatically to form a cliff or scarp several kilometers high, one of the most striking topographic features on Venus. Ishtar Terra itself is a complex highland region, roughly the size of Australia, with several distinct subregions. Lakshmi Planum is a vast elevated plateau, about 2,000 kilometers across and 3 to 4 kilometers above the mean elevation, surrounded by mountain ranges on all sides. The plateau's interior is remarkably flat, filled with lava flows that create a smooth surface. How Lakshmi Planum formed remains uncertain. It might be a large volcano, though it lacks a central caldera. Alternatively, it could be a tectonic plateau, uplifted by mantle dynamics and subsequently resurfaced by volcanism. Aphrodite Terra is the largest highland region, straddling the equator and extending for more than 10,000 kilometers west to east. It's a complex terrain including rifts, mountains, tesserae, and volcanic features. Aphrodite appears to be a zone of upwelling in Venus's mantle, where hot material rises and causes extensive volcanism and deformation. The region shows evidence of recent geological activity, with relatively few impact craters and many fresh-looking volcanic flows. These surface features collectively paint a picture of a geologically dynamic world, even without Earth-style plate tectonics. Venus has active volcanism, tectonic deformation, and surface renewal processes. The lack of mobile plates doesn't mean the planet is geologically dead. Rather, it means heat loss and surface deformation occur through different mechanisms than on Earth. Understanding these processes helps us understand not only Venus, but also other stagnant lid planets, including early Earth before plate tectonics initiated, and numerous rocky exoplanets that likely lack plate tectonics. The variety of surface features on Venus is testament to the complex interplay between the planet's interior heat, its thick lithosphere, and the absence of water. Each feature type tells part of the story of how Venus works, how it loses heat, how its mantle convects, how magma reaches the surface, and how stress in the lithosphere gets relieved. Future high-resolution mapping and detailed geophysical measurements will allow scientists to piece together this story more completely, understanding the full range of geological processes operating on Earth's enigmatic twin. Counting craters is the primary method for determining surface age on planets without samples to date radiometrically. Impact craters accumulate over time as asteroids and comets strike the surface. The older a surface, the more craters it should have, assuming a constant impact rate. From the number and size distribution of craters on Venus, scientists estimate the average surface age is between 150 million and 1 billion years. This is young compared to the 4.5 billion year age of the solar system. Something reset Venus's surface relatively recently in geological terms. What could resurface an entire planet? The most straightforward answer is global volcanic activity. The volcanic plains were laid down by extensive lava flows that buried the older, more heavily cratered surface. But the mechanism and timing of this resurfacing are controversial. Two main hypotheses exist: catastrophic global resurfacing and equilibrium resurfacing. The catastrophic resurfacing hypothesis proposes that Venus underwent a planet-wide volcanic event about 300 to 500 million years ago. In this scenario, Venus had been in a stagnant lid state with a thick, immobile lithosphere insulating the interior. Heat built up in the mantle over hundreds of millions of years because the planet lacked an efficient cooling mechanism. Eventually, the lithospheric lid became gravitationally unstable and foundered, sinking into the mantle. This triggered a massive episode of volcanism as the hot mantle was exposed and decompressed, causing widespread melting. Over a period of perhaps 10 to 100 million years, volcanic eruptions resurfaced most or all of the planet, burying the old cratered surface under fresh lava. After this catastrophic event, the lithosphere stabilized again, and volcanic activity declined to a low level. Evidence supporting catastrophic resurfacing includes the statistically random distribution of craters on Venus. If volcanic activity were ongoing and variable across the surface, we would expect some regions to have more craters and some to have fewer, with old surfaces showing higher crater densities. Instead, craters appear randomly distributed, suggesting the surface was reset globally at roughly the same time. Additionally, the small number of embayed or deformed craters suggests that little volcanic or tectonic activity has occurred since most craters formed. The equilibrium resurfacing hypothesis argues that volcanic activity on Venus is ongoing, occurring at a rate that balances crater formation with crater obliteration. In this view, volcanoes erupt frequently but locally, covering old terrain with new lava. Over time, all surfaces get renewed, maintaining a statistically uniform age. The crater distribution appears random not because of a single global event, but because of many small-scale events occurring randomly in space and time. This model suggests Venus is more geologically active than the catastrophic hypothesis implies. Recent discoveries strongly favor ongoing volcanic activity, supporting a version of equilibrium resurfacing. In 2023, scientists comparing Magellan radar images taken 8 months apart in 1991 identified a volcanic vent that changed shape and doubled in size during that hour interval. This is direct evidence of an active eruption occurring while Magellan was in orbit. The vent, located on the northern flank of Mont Mons, expanded from about 2 square kilometers to over 4 square kilometers. New lava appears to have filled the vent and spilled over the surrounding area. A 2024 study found evidence of 2 additional active volcanic eruptions in Magellan data, both on the volcano Sif Mons. These discoveries confirm that Venus is volcanically active today. The volcanic activity may not be as vigorous as during a hypothesized global resurfacing event, but it's real and ongoing. Volcanoes on Venus are erupting now, altering the surface, releasing gases into the atmosphere, and demonstrating that the planet's interior is still hot and dynamic. Why is Venus so volcanic? Part of the answer lies in its size and heat budget. Venus is nearly Earth-sized, and radioactive decay of elements like uranium, thorium, and potassium in the mantle provides a substantial heat source. This heat must escape. On Earth, heat escapes primarily through plate tectonics. Oceanic crust forms at mid-ocean ridges, cools as it spreads away, and eventually subducts at trenches, carrying heat into the deep mantle. This conveyor belt efficiently removes heat from the interior. Venus lacks plate tectonics, but it still needs to cool. Without moving plates, heat escapes primarily through volcanism. Mantle plumes rise to the surface, melt, and erupt, carrying heat upward. This hotspot volcanism is less efficient than plate tectonics at cooling the planet, which may lead to episodic behavior. Heat builds up until the lithosphere fails, triggering extensive volcanism, then stabilizes again. Alternatively, the volcanism could be more continuous but spatially concentrated in regions where the lithosphere is thin, such as at coronae and rift zones. Another factor contributing to Venus's volcanism is the high surface temperature. The extreme heat makes the lithosphere weaker and thinner than it would be on a cooler planet. A thin lithosphere is more easily penetrated by rising magma, facilitating volcanic eruptions. The lithosphere on Venus is estimated to be only 10 to 20 kilometers thick in volcanically active regions, compared to 70 to 150 kilometers for Earth's oceanic lithosphere. The lack of water also plays a role. Water lowers the melting point of rock, making it easier to generate magma. However, it also makes magma more explosive. Explosive volcanism, like that at Mount St. Helens or Pinatubo, occurs when dissolved gases violently expand as magma rises to the surface. On Venus, with essentially no water in the mantle, magmas are drier and likely erupt more effusively, producing lava flows rather than explosive eruptions. This results in the extensive lava plains and large shield volcanoes observed. Volcanic gases on Venus are predominantly CO2, based on atmospheric composition and equilibrium thermodynamic models. Small amounts of sulfur, dioxide, carbon monoxide, and other gases are also released. These gases replenish the atmosphere, compensating for loss to space and reactions with surface rocks. Without ongoing volcanism, Venus's atmosphere would slowly deplete, particularly of sulfur compounds that form the clouds. The persistence of sulfur dioxide in the atmosphere, despite its rapid destruction by photochemical reactions, indicates active volcanic outgassing. The connection between volcanism and climate is important. Volcanic eruptions release CO2 and other greenhouse gases. On Earth, volcanic CO2 is removed by weathering over timescales of hundreds of thousands to millions of years. On Venus, with no liquid water, there's no weathering to remove CO2. Every molecule of CO2 emitted by a volcano stays in the atmosphere indefinitely. Over 4.5 billion years, Venus has outgassed a massive amount of CO2, building the thick atmosphere we observe today. The volcanic activity that created the extensive lava plains and thousands of volcanoes also created the thick, hot atmosphere. Understanding Venus's volcanism is critical for understanding its evolution. Volcanic activity shapes the surface, affects the atmosphere, and provides a window into the planet's interior. The recent discoveries of active eruptions demonstrate that Venus is not a dead world, but a dynamic planet where geological processes continue to operate. Future missions will monitor volcanic activity in real time, measure the composition of volcanic gases, and determine how volcanic heat flow varies across the surface. This information will help us understand how Venus loses heat, why it lacks plate tectonics, and how its interior differs from Earth's despite their similar sizes. The missing plates. One of the most fundamental differences between Earth and Venus is the presence or absence of plate tectonics. On Earth, the lithosphere, the rigid outer shell, including the crust and uppermost mantle, is broken into about a dozen major plates and many smaller ones. These plates move, driven by convection in the mantle below. Plates diverge at mid-ocean ridges, where new crust forms. They converge at subduction zones, where old crust sinks back into the mantle. They slide past each other at transform faults. This constant motion shapes Earth's surface, creating mountain ranges, ocean basins, earthquakes, and volcanoes. Plate tectonics recycles material, regulates atmospheric composition, and enables the long-term habitability of our planet. Venus has none of this. Its surface shows no evidence of large-scale plate boundaries. no equivalent of Earth's mid-ocean ridges or subduction zones. The surface deformation is complex and varied, with fractures, folds, and volcanism, but it doesn't form a connected global network of plate boundaries. Venus appears to have a stagnant lid, a single unbroken lithospheric shell that doesn't break apart and move in the way Earth's plates do. Why this difference? Both planets are similar in size and composition. Both have hot interiors that drive geological activity, yet their surface tectonics are fundamentally different. Understanding why Venus lacks plate tectonics is one of the major questions in comparative planetology. Several factors contribute to the absence of plate tectonics on Venus. The most important is the lack of water. Water may seem irrelevant to the solid rock processes of plate tectonics, but it plays a crucial role. Water dissolved in minerals lowers their melting points and makes them weaker and more ductile. The presence of water in subducting oceanic crust facilitates melting in the overlying mantle wedge, producing the arc volcanism seen at subduction zones like the Andes or the Cascades. Water also makes rocks more prone to brittle fracture, which is necessary for the lithosphere to break into plates. On Venus, the crust and uppermost mantle are bone dry. Without water, rocks are stronger and more resistant to deformation. The lithosphere is more rigid, making it difficult for plates to form and move. Additionally, the high surface temperature on Venus makes the lithosphere thinner and weaker, but paradoxically, this may inhibit plate tectonics. A thin, weak lithosphere deforms diffusely rather than breaking into discrete plates. On Earth, the relatively cool, thick oceanic lithosphere can become dense enough to sink into the mantle, initiating subduction. On Venus, the thin lithosphere may not achieve sufficient negative buoyancy to subduct. The absence of oceans also matters. On Earth, oceanic crust forms at mid-ocean ridges, cooling by contact with seawater. This cooling creates a strong thermal gradient and contributes to the plate's density and rigidity. On Venus, without oceans, the surface cools more slowly through radiation and conduction, resulting in a different thermal structure that may not favor plate formation. Another factor is the strong gravity and slow rotation. Venus's surface gravity is 91% of Earth's, high enough that mantle convection patterns might differ from Earth's. The extremely slow rotation means the Coriolis effect, which influences the geometry of convection patterns on rapidly rotating planets, is negligible on Venus. Convection on Venus might organize differently, perhaps in a more spherically symmetric pattern that doesn't create the linear upwelling and downwelling zones that drive plate tectonics on Earth. Some researchers have proposed that Venus once had plate tectonics but lost it. If Venus had oceans early in its history, the presence of water might have enabled plate tectonics to operate. As the oceans evaporated and the water was lost, plate tectonics would have shut down, transitioning Venus to a stagnant lid. This hypothesis is speculative and difficult to test, but it's consistent with the idea that Venus underwent a transition from a more Earth-like state to its current extreme condition. Evidence for or against past plate tectonics? On Venus is ambiguous. The tesserae highlands show intense deformation that some interpret as evidence of ancient tectonic activity, possibly even plate convergence. Others argue the deformation patterns are not consistent with plate boundaries and reflect different processes, perhaps related to mantle plumes or lithospheric overturn. Without samples to date or detailed geophysical measurements, we can't definitively determine whether Venus ever had mobile plates. Recent analysis of Magellan data has revealed that Venus's lithosphere is not entirely immobile. Researchers identified 58 distinct blocks in the lowland regions that appear to have moved relative to one another. These blocks are defined by patterns of ridges and grooves that outline their boundaries. The largest block is comparable in size to Alaska. The existence of these blocks suggests that Venus's lithosphere is more mobile than a completely stagnant lid, but less mobile than Earth's full-plate tectonics. Some scientists refer to this as a squishy lid regime, where the lithosphere is weak enough to deform locally but not organized into a global network of plates. The coronae and rift zones on Venus provide additional evidence of tectonic activity. Coronae, as discussed earlier, form above mantle plumes. Their concentric fracture patterns indicate extension as do surface domes upward, followed by subsidence. Some coronae show evidence of localized subduction, where portions of the lithosphere appear to be sinking into the mantle. If this interpretation is correct, Venus has small-scale, localized subduction zones that don't connect into a global plate system. Beta Regio and Atla Regio are two large volcanic rises associated with extensive rift systems. These regions show linear fractures extending for thousands of kilometers, similar to Earth's continental rift valleys, like the East African Rift. Volcanism and tectonism are intimately linked in these areas. The rifts may represent incipient plate boundaries, places where the lithosphere is beginning to pull apart. However, these rifts don't appear to be actively spreading in the way Earth's mid-ocean ridges spread. They may represent failed rifts that never developed into full-spreading centers. The method by which Venus loses heat from its interior has major implications for its geological evolution. Earth loses most of its heat through plate tectonics. The creation of new crust at ridges and the subduction of old crust at trenches efficiently transport heat from the interior to the surface. On Venus, heat loss must occur through other mechanisms. Hotspot volcanism, as seen at coronae and large shield volcanoes, is one mechanism. Heat is carried upward by mantle plumes and released through volcanic eruptions. Another possibility is that Venus undergoes periodic lithospheric overturn. In this model, heat builds up beneath the stagnant lithosphere over hundreds of millions of years. Eventually, the thick lithosphere becomes denser than the underlying hot mantle and gravitationally unstable. It founders, sinking en masse into the mantle and being replaced by hot mantle material rising to form new lithosphere. This catastrophic overturn would produce a global resurfacing event, consistent with the young surface age. After overturn, the system would stabilize, heat would build up again, and the cycle would repeat. Each cycle might last 500 million to 1 billion years. Whether Venus undergoes periodic overturn or maintains a more continuous but episodic level of volcanic activity remains debated. The recent discoveries of active volcanism suggest that Venus is not in a completely quiescent phase between overturns, but rather experiences ongoing activity. Detailed monitoring over the coming decades will help resolve this question. The absence of plate tectonics on Venus has profound implications for the planet's habitability, both past and present. On Earth, plate tectonics is essential for maintaining a stable climate over geological timescales. The weathering carbonate cycle, which regulates atmospheric CO2, depends on the continuous renewal of surface rocks through plate motions. Subduction carries carbonates into the mantle, where they decompose, releasing CO2 that returns to the atmosphere through volcanism. This cycle keeps CO2 levels balanced. On Venus, without this cycle, CO2 accumulates in the atmosphere, leading to the runaway greenhouse. Plate tectonics also creates diverse environments on Earth: continental shelves, deep ocean basins, volcanic arcs, mid-ocean ridges. Each environment hosts distinct ecosystems. The cycling of nutrients through subduction and volcanism is thought to be important for life. Some scientists argue that plate tectonics is necessary for a planet to remain habitable over billions of years. If true, the absence of plate tectonics on Venus might have been a contributing factor to its loss of habitability beyond just the proximity to the Sun. Understanding why Venus lacks plate tectonics informs our assessment of exoplanet habitability. Many rocky exoplanets likely lack plate tectonics, especially those that are dry or tidally locked to their stars. If plate tectonics is indeed necessary for long-term habitability, then many potentially habitable exoplanets may actually be more Venus-like than Earth-like. Conversely, if Venus once had plate tectonics and lost it, that suggests plate tectonics is not a permanent feature and could shut down on other planets, including Earth in the distant future as our planet cools and the mantle becomes more viscous. A day longer than a year. Venus rotates on its axis in the opposite direction from most planets in the solar system. This retrograde rotation means that from Venus's north pole, the planet spins clockwise, while Earth and most other planets spin counterclockwise. On Venus, the sun rises in the west and sets in the east, the reverse of what we experience on Earth. This backward spin is one of Venus's most peculiar features, and its origin remains one of planetary science's enduring mysteries. The rotation is not only backward, but incredibly slow. Venus takes 243.0185 Earth days to complete one rotation relative to the stars. This is called the sidereal day. To put this in perspective, Mercury, the next slowest rotating planet, has a sidereal day of 58.6 Earth days. Earth rotates once every 23 hours and 56 minutes. Venus's rotation is more than 200 times slower than Earth's. It's the slowest spinning planet in the solar system. Adding to the peculiarity, Venus's rotation period is longer than its orbital period. Venus orbits the Sun once every 224.7 Earth days. This means a Venusian year is shorter than a Venusian day. If you stood on Venus and watched the stars, you would see them complete one full circle around the sky before Venus completed one orbit around the Sun. In most planetary systems, days are much shorter than years. Venus is the exception. The combination of retrograde rotation and orbital motion creates an interesting effect on the solar day, the time from sunrise to sunrise. Because Venus is rotating backward relative to its orbital motion, the orbital motion effectively speeds up the apparent motion of the Sun across the sky. A solar day on Venus lasts about 116.75 Earth days, roughly half a Venusian year. This means there are almost exactly 2 sunrises and 2 sunsets during one Venusian orbit. Each day and each night lasts nearly 2 Earth months. Imagine standing on Venus's surface, protected somehow from the heat and pressure. The Sun would rise slowly in the west, taking weeks to climb to its zenith. The day would continue for another 2 months as the Sun descended toward the eastern horizon. Then would come nearly 2 months of darkness before the sun rose again in the west. The long days and nights would be remarkable, though in reality the thick atmosphere on Venus creates a diffuse illumination that would make the day-night transition gradual and unclear from the surface. How did Venus acquire this bizarre rotation? When planets form from the protoplanetary disk, they typically inherit the rotation direction of the disk, which is the same as their orbital direction. All planets should naturally rotate prograde, spinning in the same direction they orbit. Venus must have been altered after formation. Two main hypotheses explain the retrograde rotation: a giant impact scenario and tidal and atmospheric evolution. The giant impact hypothesis proposes that Venus, like most planets, initially rotated prograde with a period of perhaps 10 to 20 hours, similar to Earth's rotation. Early in the solar system's history, a massive body, perhaps half the size of Venus or larger, collided with the planet. The impact was so violent that it reversed Venus's rotation, flipping the planet or transferring enough angular momentum to slow and eventually reverse the spin. Such impacts were common during the late stages of planetary formation. Earth's moon is thought to have formed from debris ejected by a giant impact between Earth and a Mars-sized body. A similar event could have affected Venus. If Venus was struck by a giant impactor, there should be some evidence remaining. On Earth, the giant impact that formed the moon left a signature in our planet's rotation rate and axial tilt. Venus's slow retrograde rotation could be the signature of its impact. Additionally, such an impact might have stripped Venus of any primordial moon it possessed. Venus has no moons today, unlike Earth and Mars, which both have satellites. The absence of a moon is consistent with a violent impact that disrupted any existing moons and failed to produce debris that could coalesce into new ones. However, the giant impact hypothesis has challenges. Computer simulations show that reversing a planet's rotation through impact requires very specific conditions. The impact must be nearly head-on and involve a body of just the right size. If the impactor is too small, it won't reverse the rotation. If too large, it would catastrophically disrupt Venus, possibly ejecting material that forms a debris disk or causing the planet to reaccrete entirely. Finding the right impact scenario that produces Venus's current rotation without other detectable effects is difficult. The alternative hypothesis involves tidal forces and atmospheric effects evolving over billions of years. Venus is close enough to the Sun that solar tides on the planet are significant. Tides raised by the Sun create bulges in Venus's solid body and atmosphere. These bulges lag behind the Sun's position due to friction and viscous effects. The gravitational pull of the Sun on these in-offset bulges exerts a torque on Venus, gradually slowing its rotation. Over billions of years, this tidal dissipation could slow Venus from an initially fast prograde rotation to zero, then continue into retrograde rotation until an equilibrium is reached. Venus's thick atmosphere plays a role in this process. The massive atmosphere, with a mass about 90 times Earth's atmospheric mass, is subject to thermal tides driven by solar heating. The day side of the atmosphere heats up and expands, creating pressure gradients that drive winds. These thermal tides create torques on the solid planet. Computer models show that the combined effects of solar gravitational tides and atmospheric thermal tides can slow and reverse a planet's rotation over billions of years. Venus's current slow retrograde rotation represents an approximate equilibrium between these tidal forces. This tidal evolution hypothesis doesn't require a giant impact, making it more elegant in some ways. It also explains why Venus's rotation period is close to a resonance with Earth. Every 584 days, when Venus and Earth are closest in their orbits, Venus presents nearly the same face toward Earth. This is a 5.1 resonance between Venus's solar day and the synodic period of Earth and Venus. Whether this resonance is coincidental or has dynamical significance is debated, but it suggests that Earth's tidal influence on Venus might also play a minor role in the evolution of Venus's rotation. The slow rotation has significant effects on Venus's atmospheric circulation. On rapidly rotating planets like Earth, the Coriolis effect strongly influences wind patterns, creating zonal jet streams and cyclonic storms. On slowly rotating Venus, the Coriolis effect is weak. The atmosphere circulates in a simpler pattern dominated by solar heating and global-scale Hadley cells. This contributes to the superrotation of the upper atmosphere, where winds race around the planet much faster than the surface rotates. The slow rotation also affects Venus's magnetic field, or rather the lack thereof. Planetary magnetic fields are generated by dynamo action in the liquid metal cores of planets. The dynamo requires convection in the core and sufficient rotation to organize the convective motions. Earth's relatively fast rotation helps generate its strong magnetic field. Venus's slow rotation may be insufficient to sustain a dynamo, even if convection occurs in the core. Alternatively, if Venus's core has solidified or is not actively convecting, no dynamo would operate regardless of rotation rate. Measuring Venus's rotation rate with high precision has been a challenge. Early observations suggested a range of periods, and even after radar measurements in the 1960s established the approximate 243-day period, small variations were detected. Recent studies using radar observations over many years have measured Venus's rotation rate to within about 0.01%. The measurements show that the rotation rate is not constant, but fluctuates slightly over time. These fluctuations, on the order of a few minutes over decades, may be caused by exchanges of angular momentum between the solid planet and the atmosphere. The massive atmosphere can speed up or slow down the solid planet's rotation through friction, especially during global atmospheric oscillations or circulation changes. Understanding Venus's rotation is important for future missions. Knowing the precise rotation rate and its variations is necessary for accurate targeting when landing spacecraft on the surface. A small error in rotation rate translates to a significant error in the predicted location of landing sites. The Da Vinci mission, which will send a probe through Venus's atmosphere to image the Tesserae Highlands, requires precise knowledge of Venus's rotation to ensure the probe captures images of the intended target. Ongoing radar observations from Earth continue to refine the rotation rate and track its variations. The mystery of Venus's retrograde rotation illustrates how much we still don't understand about planetary evolution. Whether Venus's rotation resulted from a giant impact or from billions of years of tidal evolution remains uncertain. Future missions might find clues in the planet's interior structure or in the detailed patterns of surface deformation. For now, Venus's backward slow rotation stands as one of the planet's many peculiarities, a reminder of the complex and sometimes violent processes that shape planetary systems. Decades of exploration. Humanity's exploration of Venus spans more than half a century, with dozens of missions attempting to pierce the planet's secrets. These missions transformed Venus from a mysterious, shrouded world into a place we understand in remarkable detail. Though many questions remain, the history of Venus exploration is a story of technological challenges, surprising discoveries, and international cooperation. The space age began in 1957 with the launch of Sputnik 1, and within just 5 years, spacecraft were attempting to reach Venus. The Soviet Union launched Venera 1 in February 1961, the first spacecraft to target another planet. Venera 1 lost contact en route, but passed within about 100,000 kilometers of Venus in May 1961. Although it returned no data, it demonstrated that interplanetary travel was possible. In December 1962, NASA's Mariner 2 flew past Venus at a distance of 3,433 kilometers, becoming the first successful interplanetary mission. Mariner 2 carried instruments to measure Venus's temperature, magnetic field, and charged particle environment. The mission confirmed the high surface temperatures indicated by earlier radio observations, finding that Venus was much hotter than any scientist had expected. Mariner 2 also found that Venus had no significant magnetic field and rotated slowly. The success of Mariner 2 proved that spacecraft could survive the journey to other planets and return valuable scientific data. The Soviet Union continued its assault on Venus throughout the 1960s with a series of Venera probes. Venera 4, launched in June 1967, was the first spacecraft to enter another planet's atmosphere and return data. The probe descended by parachute through Venus's atmosphere, measuring temperature, pressure, and composition. The data revealed that the atmosphere was predominantly carbon dioxide and far denser than expected. Venera 4's instruments failed at an altitude of about 25 kilometers above the surface, overwhelmed by the extreme conditions. Scientists initially thought the probe had reached the surface, but analysis of the data showed it had been crushed by pressure long before reaching the ground. Venera 5 and 6 in 1969 were designed to withstand higher pressures, but they too failed to reach the surface, succumbing to the crushing atmosphere at altitudes of about 20 kilometers. The Soviet engineers learned from each failure, steadily improving their designs. Venera 7, launched in August 1970, was built like a submarine to withstand immense pressure. On December 15, 1970, Venera 7 successfully reached the surface and transmitted data for 23 minutes before its electronics failed. This was the first successful landing on another planet. Venera 7 measured a surface temperature of 474 degrees Celsius and pressure of 90 atmospheres, confirming Venus's hellish conditions. Venera 8 in 1972 survived for 50 minutes on the surface, measuring light levels and gamma-ray emissions from surface rocks. The measurements indicated the surface was basaltic, similar to Earth's volcanic rock. Venera 9 and 10 in 1975 carried cameras. After descending to the surface, each lander opened protective covers and captured the first images from another planet's surface. The images showed a rocky landscape littered with flat stones and fragments, illuminated by the dim orange light filtering through the clouds. The rocks appeared angular and relatively unweathered, consistent with a volcanically active world where erosion is slow. The Venera 9 and 10 landers operated for about an hour each before succumbing to the heat. The images they returned stunned the world. For the first time, humanity could see the surface of another planet in situ. The images showed a landscape that was alien yet strangely familiar, with rocks of various sizes and gentle slopes extending to the horizon. Venera 11 and 12 in 1978 carried improved instruments and measured lightning-like electrical discharges in the atmosphere, though the interpretation of these signals as lightning remains controversial. Venera 13 and 14 in 1981 landed successfully and returned color images of the surface. The images showed orange-brown rock fields under a hazy orange sky. Venera 13 survived for 127 minutes, the longest survival time of any Venus lander, and drilled a soil sample for chemical analysis. The data indicated the surface was basaltic, confirming earlier findings. NASA returned to Venus with the Pioneer Venus mission in 1978. Pioneer Venus consisted of 2 spacecraft, an orbiter and a multi-probe mission. The orbiter mapped Venus's surface with radar and measured its gravitational field. It operated for 14 years, far beyond its designed 1-year mission before its orbit decayed and it entered Venus's atmosphere in 1992. The multi-probe mission released 4 probes into Venus's atmosphere at different locations. The large probe descended by parachute, while 3 smaller probes descended without parachutes. All 4 probes transmitted data during their descents, providing vertical profiles of temperature, pressure, composition, and cloud properties. The Pioneer Venus missions revealed the layered structure of Venus's atmosphere and provided detailed measurements of cloud composition. They detected sulfuric acid aerosols and found that the clouds consist of 3 main layers between 45 and 70 kilometers altitude. The missions also provided the first complete radar map of Venus, revealing large highland regions like Ishtar Terra and Aphrodite Terra, and many volcanic features. In the 1980s, the Soviet Union sent Venera 15 and 16, orbiters equipped with radar, to map the northern hemisphere of Venus. These missions provided higher resolution images than Pioneer Venus, revealing details of surface features. In 1985, the Vega 1 and 2 missions, launched to intercept Halley's Comet, stopped at Venus en route. Each mission released a lander and a balloon. The balloons floated in Venus's atmosphere at an altitude of about 54 kilometers for 2 days, drifting with the winds and measuring atmospheric properties. This was the first use of aerial platforms in another planet's atmosphere. The most ambitious Venus mission came in 1989 with NASA's Magellan spacecraft. Launched from the space shuttle Atlantis, Magellan arrived at Venus in August 1990 and began radar mapping. Using synthetic aperture radar, Magellan created high-resolution images of the surface, achieving resolutions of 100 to 250 meters, far better than any previous mission. Over 4 years, Magellan mapped 98% of Venus's surface, generating images that remain the most detailed views of the planet to this day. Magellan revealed a world dominated by volcanism and tectonic deformation. The mission discovered pancake, domes, coronae, arachnoids, and vast lava plains. It identified thousands of volcanoes and mapped the planet's topography in detail. Magellan also measured Venus's gravitational field by tracking the spacecraft's orbit, providing information about the planet's interior structure. In 1993, Magellan pioneered aerobraking, dipping into Venus's upper atmosphere to slow down and circularize its orbit using atmospheric drag. This technique has been used by many subsequent missions to other planets. At the end of its mission in October '94, Magellan was commanded to plunge into Venus's atmosphere collecting data on atmospheric density during its descent before contact was lost. The spacecraft likely disintegrated and vaporized at an altitude of about 30 kilometers, ending one of NASA's most successful planetary missions. After Magellan, Venus exploration entered a lull. Mars became the primary target for planetary missions during the 1990s and 2000s. However, in 2005, the European Space Agency launched Venus Express, which arrived at Venus in April 2006. Venus Express studied Venus's atmosphere in detail using infrared and ultraviolet instruments. It observed the planet's cloud patterns, measured the super-rotating winds, and studied the interaction between Venus's atmosphere and the solar wind. Venus Express discovered that Venus has a long ion tail extending millions of kilometers downwind, similar to a comet's tail. Venus Express also made infrared observations of the surface through gaps in the clouds, providing limited compositional information. The mission operated for 8 years, far exceeding its designed 2-year lifespan, before its orbit decayed and contact was lost in December 2014. The spacecraft likely entered the atmosphere and disintegrated. Japan's Akatsuki spacecraft was launched in 2010, but failed to enter orbit around Venus on its first attempt. The spacecraft spent 5 years in solar orbit before making a second successful attempt to enter Venus orbit in December 2015. Akatsuki has been studying Venus's atmospheric dynamics, observing the superrotation and identifying giant gravity waves in the atmosphere. The mission detected a large stationary wave in the atmosphere, possibly the largest gravity wave in the solar system, stretching 10,000 kilometers and persisting for days. Akatsuki continued operating until late 2024, when contact with the spacecraft was lost. These missions collectively transformed our understanding of Venus. They revealed a planet of extremes, the hottest surface in the solar system, a crushing atmosphere, sulfuric acid clouds, and a young surface shaped by extensive volcanism. They showed that Venus is geologically active, with ongoing volcanic eruptions and atmospheric circulation patterns, unlike those on any other planet. The data from these missions continue to be analyzed, yielding new discoveries decades after the spacecraft ceased operations. Looking back at Venus exploration, several lessons emerge. First, Venus is extraordinarily challenging to explore. The high temperature and pressure destroy spacecraft quickly. The longest any lander has survived on Venus's surface is just over 2 hours. Future surface missions will require advanced materials and cooling systems. Second, radar is essential for mapping Venus's surface through the thick clouds. Every successful surface mapping mission has used radar. Optical imaging from orbit is impossible due to the cloud cover. Third, Venus rewards persistence. Many missions failed completely, but the successful missions have returned immense amounts of valuable data. The history of Venus exploration is also a testament to international cooperation and competition. The Soviet Union and the United States pursued parallel programs during the Cold War, each achieving remarkable successes. Soviet engineers pioneered landing technology that could survive Venus's surface, while American engineers perfected orbital radar mapping. European and Japanese missions added atmospheric studies and long-term monitoring. Future missions will continue this tradition, with NASA and ESA both planning ambitious return to Venus in the coming decade. Venus today, an active world. For decades, scientists debated whether Venus is currently geologically active. The planet's young surface suggested recent or ongoing volcanism, but direct evidence was lacking. Without seismic sensors on the surface to detect Venus quakes or long-term monitoring of surface changes, confirming active volcanism was difficult. This changed dramatically in 2023 with a stunning discovery in archival data from the Magellan mission. Robert Herrick, a research professor at the University of Alaska Fairbanks, spent more than 200 hours manually comparing Magellan radar images taken at different times during the mission. He was looking for changes in surface features that might indicate volcanic eruptions or lava flows. What he found was dramatic. A volcanic vent on the northern flank of Mat Mons had changed shape and doubled in size over an 8-month period in 1991. The vent initially appeared as a roughly circular depression about 2 square kilometers in area. 8 months later, in a subsequent Magellan Pass over the same region, the vent had grown to more than 4 square kilometers. Its shape had changed from circular to irregular, and the floor appeared filled with fresh material, likely new lava. The vent walls also appeared degraded, possibly from collapse or from lava overflowing. These changes are consistent with an active volcanic eruption occurring while Magellan was in orbit. This discovery, published in the journal Science in March 2023, provided the first direct evidence of active volcanism on Venus. It demonstrated that Venus is not just a planet with a young surface from past activity, but a world where volcanic eruptions occur today. The eruption on Mat Mons likely released lava onto the surface and injected gases into the atmosphere, processes that continue to shape Venus. The discovery prompted renewed examination of Magellan data. In 2024, a team led by Italian researchers analyzed radar images of 2 other volcanoes, Sif Mons and Aza Mons, finding evidence of additional active eruptions. These volcanoes showed changes in surface brightness and texture consistent with new lava flows emplaced between Magellan's mapping cycles. The 2024 study, published in Nature Astronomy, reported 2 eruptions, providing further confirmation that Venus experiences multiple active volcanic events. The frequency of eruptions appears to be low, perhaps a few per century, but the planet is undeniably active. These discoveries vindicate earlier findings from Venus Express. The European orbiter detected transient increases in sulfur dioxide concentrations in Venus's atmosphere between 2006 and 2012. Sulfur dioxide is a volcanic gas, and the variations were interpreted as possible evidence of volcanic eruptions injecting fresh SO2 into the atmosphere. However, without direct observation of surface changes, the interpretation remained speculative. The Magellan discoveries confirm that volcanism is indeed ongoing, and that atmospheric variations likely reflect active volcanic outgassing. Why is this important? Active volcanism tells us Venus's interior is still hot and convecting. The planet is losing heat through volcanic eruptions, transporting energy from the mantle to the surface. This has implications for understanding how Venus's interior differs from Earth's. Despite lacking plate tectonics, Venus is not geologically dead. Hotspot volcanism and possibly lithospheric mobility in some regions provide mechanisms for heat loss and surface renewal. Active volcanism also affects Venus's atmosphere. Volcanic eruptions release CO2, sulfur dioxide, water vapor, and other gases. These gases replenish atmospheric constituents that are destroyed by photochemistry or lost to space. Without ongoing volcanic outgassing, Venus's atmosphere would gradually change composition. The sulfuric acid clouds, which depend on a supply of sulfur dioxide, would eventually dissipate if volcanic activity ceased. The persistence of the clouds indicates continuous or frequent volcanic input. The locations of active volcanism are also informative. The eruptions observed in Magellan data occurred at large shield volcanoes and in regions associated with mantle hotspots. This is consistent with the hypothesis that Venus's volcanism is driven by mantle plumes rising from the deep interior. These plumes melt as they reach lower pressures, producing magma that erupts at the surface. The concentration of volcanism at specific locations suggests the mantle beneath Venus is heterogeneous, with some regions hotter and more active than others. Another line of evidence for ongoing geological activity comes from studies of Venus's coronae. Analysis of gravity and topography data reveals that many coronae are located in regions where the lithosphere is thin, estimated at only 10 to 20 kilometers thick. Thin lithosphere implies high heat, flow, and active mantle upwelling. The coronae appear to be sites where mantle plumes are currently rising, doming the surface and causing volcanism and tectonic deformation. These regions may be analogous to Earth before the onset of plate tectonics, providing a window into how rocky planets behave in a pre-plate tectonic regime. Recent modeling studies suggest Venus's tectonic regime may be more complex than a simple stagnant lid. The lithosphere appears broken into blocks or partially mobile in some regions, particularly in the lowland plains. This squishy lid or sluggish lid regime allows for localized deformation and possibly small-scale convection in the lithosphere. The surface is not as mobile as Earth's tectonic plates, but it's not completely rigid either. This intermediate state may explain both the young surface age and the evidence for ongoing activity. The discovery of active volcanism has implications for the possibility of life. If Venus's clouds harbor microbial life, as some speculative hypotheses suggest, volcanic eruptions could transport microbes from the lower atmosphere or even from subsurface environments into the clouds. Conversely, eruptions could introduce materials that support microbial metabolism, such as sulfur compounds or trace amounts of water vapor. While the existence of life on Venus remains highly speculative and unsupported by evidence, active volcanism keeps the possibility slightly more plausible than if the planet were geologically dead. Monitoring Venus's volcanic activity will be a priority for future missions. Real-time detection of eruptions would allow scientists to study the processes as they occur, measuring gas emissions, observing lava flows, and tracking how eruptions affect the atmosphere. Current and future missions will carry instruments capable of detecting thermal anomalies, changes in surface elevation, and variations in atmospheric composition that signal volcanic activity. Over time, scientists hope to compile a catalog of Venus's active volcanoes and determine how frequently eruptions occur. The recognition that Venus is currently active transforms how we think about the planet. Venus is not a static museum of past geological processes, but a dynamic world where change is ongoing. Every few years or decades, new lava flows erupt onto the surface, altering the landscape. Gases rise from the interior, affecting the atmosphere. Tectonic forces continue to deform the crust. Venus is alive, geologically speaking, and understanding this active geology is key to understanding the planet's evolution and current state. The next chapter. After the end of the Magellan and Venus Express missions, Venus exploration entered a quiet period. For more than a decade, no new missions were launched to Venus. The focus shifted to Mars, with multiple rovers and orbiters studying the red planet in unprecedented detail. But Venus's importance never diminished, and in recent years, interest in our sister planet has surged. Multiple agencies are planning missions to return to Venus in the coming decade, missions that promise to answer long-standing questions and reveal new mysteries. In June 2021, NASA announced the selection of 2 Venus missions as part of its Discovery program, Da Vinci and Veritas. These missions represent the first NASA spacecraft to visit Venus since Magellan in the early 1990s. Both missions aim to understand why Venus and Earth, which started so similarly, evolved into such different worlds. Da Vinci, which stands for Deep Atmosphere, Venus Investigation of Noble Gases, Chemistry, and Imaging, will study Venus's atmosphere in unprecedented detail. The mission consists of a flyby spacecraft and a descent probe. The spacecraft will make 2 flybys of Venus, conducting remote sensing observations of the clouds and high-altitude atmosphere. During the second flyby, it will release a spherical descent probe about 1 meter in diameter. The probe will plunge into Venus's atmosphere on the day side, descending for about 1 hour before reaching the surface. During descent, it will sample the atmospheric composition, measuring the abundances of noble gases like argon, xenon, and krypton, as well as trace gases like water vapor, carbon monoxide, and hydrogen chloride. Noble gases are particularly valuable because they're chemically inert, and their relative abundances preserve information about the planet's formation and evolution. By comparing Venus's noble gas ratios to those of Earth, Mars, and meteorites, scientists can constrain how Venus formed and what materials contributed to its composition. Da Vinci will also measure the isotopic ratios of key elements, including the deuterium to hydrogen ratio, which provides information about water loss. The mission will determine more precisely how much water Venus has lost over its history. It will measure sulfur isotopes to understand the sulfur cycle and volcanic outgassing rates. It will analyze the vertical structure of the atmosphere, measuring temperature, pressure, and wind speeds at different altitudes. As the probe descends through the clouds, it will characterize the cloud particles, determining their composition, size distribution, and physical properties. This will help clarify the formation mechanisms of Venus's sulfuric acid clouds and whether the mysterious ultraviolet absorbers in the clouds are sulfur compounds, iron chloride, or something else entirely. In the final phase of descent, below the clouds, Da Vinci will activate high-resolution cameras. These cameras will capture images of the surface as the probe descends, eventually targeting the Alpha Regio Highland, one of Venus's tesserae. Tesserae are the oldest and most geologically complex terrains on Venus, possibly analogous to Earth's continents. The images will have resolutions comparable to those from an aircraft flying over Earth, potentially revealing details never before seen on Venus's surface. The probe is not designed to survive landing, but there's a chance it could transmit data for a few minutes after impact if conditions allow. The descent sphere is built to withstand the impact at about 12 meters per second, and if the electronics don't fail immediately upon landing, Da Vinci could provide the first data from Venus's surface since the Soviet Venera landers in the 1980s. Da Vinci is scheduled to launch in the early 2030s, with arrival at Venus approximately 2 years later. The mission is led by NASA's Goddard Space Flight Center and will provide the first in situ atmospheric measurements of Venus in more than 40 years. VERITAS, which stands for Venus Emissivity, Radioscience, INSAR, Topography, and Spectroscopy, is an orbiter mission designed to understand Venus's surface and interior. VERITAS will carry a state-of-the-art synthetic aperture radar, far superior to Magellan's radar, capable of imaging the surface at resolutions better than 15 meters. It will create three-dimensional topographic maps with vertical resolution of about 5 meters. These maps will reveal surface features in exquisite detail, allowing scientists to determine the ages of different terrains and understand how Venus's surface has evolved. VERITAS will also carry a near-infrared spectrometer to measure the composition of surface rocks. By observing the surface through gaps in the clouds during nighttime, when the hot surface emits infrared radiation that can penetrate the cloud deck, the spectrometer will identify different rock types. Scientists will look for signatures of granite or other rocks that form in the presence of water. Finding such rocks would provide strong evidence that Venus once had liquid water on its surface. The mission will measure Venus's gravitational field with high precision by tracking the spacecraft's orbit. Variations in the gravitational field reveal the density distribution beneath the surface, providing information about crustal thickness, mantle structure, and possibly the size and state of the core. VERITAS will also search for active volcanic eruptions by detecting thermal anomalies and surface deformation. The mission will monitor volcanoes and tectonic regions to determine which areas are currently active. VERITAS partners include Lockheed Martin Space, the Italian Space Agency, the German Aerospace Center, and France's space agency CNES. The mission was originally scheduled for launch in the late 2020s, but has been delayed to the early 2030s due to budgetary constraints and other factors. When it launches, VERITAS will revolutionize our understanding of Venus's surface geology and internal structure. The European Space Agency is also returning to Venus with the Envision mission, selected in June 2021 as part of ESA's Cosmic Vision program. Envision will complement the NASA missions by providing additional radar mapping, atmospheric studies, and subsurface sounding. The mission will carry VENSAR, a synthetic aperture radar being developed with NASA's involvement, along with spectrometers and a subsurface radar to probe the shallow subsurface of Venus. Envision will investigate whether Venus has active plate tectonics or any signs of past tectonic activity. It will search for volcanic activity by monitoring surface changes over time. It will study the interaction between Venus's surface and atmosphere, looking at how volcanic outgassing affects atmospheric composition and how the atmosphere weathers surface rocks. Envision is scheduled to launch in the early 2030s and will work in coordination with Da Vinci and VERITAS to provide a comprehensive view of Venus. Beyond these flagship missions, other smaller missions and concepts are being studied. Rocket Lab, AZ2, private aerospace company, is developing a small Venus probe to be launched on one of their Electron rockets. India's space agency ISRO is planning the Shukrayan mission, an orbiter to study Venus's atmosphere. Russia's Roscosmos has proposed Venera D, a large mission with an orbiter, lander, and possibly aerial platforms, though funding and timelines remain uncertain. These missions will address fundamental questions. Did Venus ever have oceans, and if so, for how long? What is the current rate of volcanic activity, and which volcanoes are active? Does Venus have remnants of ancient continents? What is the composition of the surface rocks? How thick is the crust? And what is the structure of the interior? Is there evidence of past or present plate tectonics? What drives the superrotation of the atmosphere? Are there organic molecules in the atmosphere or on the surface? Could any form of life exist in Venus's clouds? The technological challenges are significant. Descending through Venus's atmosphere requires heat shields capable of withstanding intense aerodynamic heating. Operating on the surface or in the lower atmosphere requires electronics that can function at temperatures exceeding 450 degrees Celsius. Communication through the thick atmosphere is difficult. Landing precision is challenging due to uncertainties in atmospheric winds and Venus's slow, variable rotation. Despite these challenges, engineers are developing new technologies, including high-temperature electronics, silicon carbide semiconductors, and advanced cooling systems. One exciting proposal involves floating platforms in Venus's upper atmosphere. At an altitude of about 50 kilometers, temperatures and pressures are Earth-like, and breathable air would naturally float in the CO2 atmosphere. A balloon or airship could float indefinitely, powered by solar panels, conducting atmospheric measurements and surface observations. The Soviet Vega balloons demonstrated this concept in 1985, floating for 2 days before their batteries expired. Modern designs could include long-duration balloons or even crude aerial habitats. While such missions are not yet funded, they represent a possible future for Venus exploration. Sample return from Venus is also being studied. Returning samples of Venus's atmosphere or surface to Earth for detailed laboratory analysis would provide invaluable data. Atmospheric samples could be collected by a probe during descent and returned in a sealed capsule. Surface samples would require a lander capable of scooping rocks or soil and launching a return vehicle from Venus's surface, an extraordinarily challenging task given the heat and pressure. No sample return mission is currently funded, but it remains a long-term goal. The next decade will be transformative for Venus science. Multiple spacecraft from different agencies will converge on Venus, each contributing unique capabilities. Da Vinci will provide in situ atmospheric data and high-resolution images of tesserae. Veritas will map the surface and interior structure. Envision will add radar mapping and subsurface sounding. Together, these missions will provide a multifaceted view of Venus, revealing how the planet works and how it evolved. We stand on the threshold of a new era of Venus exploration. After decades of neglect, Venus is once again a priority. The coming missions will transform our understanding, answering long-standing questions and undoubtedly raising new ones. Venus, our nearest planetary neighbor and Earth's twin, will finally reveal its secrets, lessons from a lost world. The story of Venus is ultimately a cautionary tale about planetary climates and the fragility of habitability. Venus began as a world not so different from Earth. Both planets formed in the same protoplanetary disk from similar materials at similar times. Both accreted water from asteroids and comets. Both likely had substantial atmospheres of CO2 and water vapor. Yet, today, One world teems with life, while the other is a lifeless inferno. Understanding what caused these divergent paths is one of the most important questions in planetary science. The primary difference was distance from the Sun. Venus orbits 28% closer to the Sun than Earth does, receiving about twice as much solar energy per square meter. This seemingly small difference placed Venus just inside the inner edge of the habitable zone, the region where liquid water can exist on a planet's surface. At Venus's orbital distance, the greenhouse effect from even a modest amount of water vapor in the atmosphere can initiate a runaway process. As temperatures rise, more water evaporates, strengthening the greenhouse effect further, leading to higher temperatures and more evaporation in a self-reinforcing cycle. On Earth, our slightly greater distance from the Sun meant that our initial conditions were cool enough for water to condense and form oceans. Once liquid oceans existed, they acted as a buffer, keeping most water in liquid form rather than vapor. The weathering carbonate cycle, enabled by liquid water, removed CO2 from the atmosphere and locked it in rocks. Plate tectonics recycled these carbonates and maintained a balanced carbon cycle. Earth's climate stabilized in a state conducive to life. Venus lacked these stabilizing mechanisms. If Venus did have oceans, they were lost relatively quickly, within the first billion years or so of the planet's history. Once the water was in the atmosphere, as vapor, photodissociation and hydrogen escape stripped it away, eliminating any possibility of returning to a temperate state. Without liquid water, silicate weathering ceased, volcanic CO2 accumulated in the atmosphere, and temperatures soared. The thick CO2 atmosphere created a greenhouse effect so intense that surface temperatures rose to levels that would melt lead. The planet crossed a threshold beyond which recovery was impossible. This narrative has profound implications for Earth's climate. Could Earth experience a runaway greenhouse effect similar to Venus? Under current or projected near-term conditions, the answer is no. Earth receives significantly less solar energy than Venus, and our Sun's luminosity increases very slowly on timescales of hundreds of millions of years. Even with significant anthropogenic CO2 emissions, Earth's climate will warm, potentially causing severe disruptions to ecosystems and human societies. But we won't trigger a runaway greenhouse effect that boils the oceans. The physics simply don't support such an outcome at Earth's orbital distance with our Sun's current luminosity. However, Venus teaches us that planetary climates have tipping points. Once certain thresholds are crossed, positive feedbacks can drive systems to new equilibrium states that are radically different and potentially irreversible on human timescales. On Venus, the loss of water was the irreversible step. Once the hydrogen escaped to space, it was gone forever. The planet couldn't return to a habitable state without a new supply of water, which is not forthcoming. Earth has its own potential tipping points, such as the loss of ice sheets, changes in ocean circulation, or methane release from permafrost and seabed clathrates. While none of these will cause Venus-like conditions, they could lead to climate states very different from today, with significant consequences for humanity and ecosystems. Venus also demonstrates the importance of water for planetary habitability. Water is essential for life as we know it, but it's also crucial for planetary climate regulation. The weathering carbonate cycle depends on liquid water. Without it, volcanic CO2 accumulates unchecked. Water in the mantle also affects tectonics, lowering melting points and enabling plate motions. A dry planet like Venus behaves differently than a wet planet like Earth, geologically and climatically. The absence of plate tectonics on Venus highlights how this process is not inevitable for rocky planets. Plate tectonics requires specific conditions: a wet mantle, sufficient cooling to create dense lithosphere, and likely other factors. Many or most rocky exoplanets may lack plate tectonics, particularly if they're dry or have thick stagnant lids. If plate tectonics is necessary for long-term habitability, as some scientists argue, then many planets may be uninhabitable despite being in the habitable zone. Venus serves as an example of a planet that could have been habitable but failed to maintain the conditions necessary for life. Studying Venus informs our search for and characterization of exoplanets. Thousands of exoplanets have been discovered, and many are rocky planets similar in size to Earth and Venus. Some orbit in the habitable zones of their stars, but determining whether these planets are actually habitable requires understanding their atmospheres and surface conditions. Many of these exoplanets likely resemble Venus more than Earth. They may have thick CO2 atmospheres, extreme greenhouse effects, and no liquid water. Learning to distinguish Earth-like planets from Venus-like planets is a major goal of exoplanet science. Several techniques are being developed to characterize exoplanet atmospheres. Transit spectroscopy, where we observe a planet passing in front of its star and analyze the starlight filtered through the planet's atmosphere, can reveal atmospheric composition. This technique has detected water vapor, carbon dioxide, methane, and other molecules in exoplanet atmospheres. For rocky planets orbiting in habitable zones, detecting CO2-dominated atmospheres versus nitrogen-oxygen atmospheres could distinguish Venus-like from Earth-like worlds. Direct imaging, where telescopes block out the star's light and capture the faint reflected light from the planet itself, is another promising technique. This allows measurement of the planet's albedo and spectrum. A very high albedo might indicate thick clouds like Venus's. Spectral features of CO2 and water vapor could be detected, helping determine atmospheric composition. Future space telescopes, like the Habitable Worlds Observatory being planned by NASA, will employ direct imaging and spectroscopy to study rocky exoplanets and search for signs of habitability or life. Understanding the frequency of Venus-like versus Earth-like planets has implications for the prevalence of life in the universe. If most rocky planets in habitable zones are actually Venus-like, with runaway greenhouse atmospheres and no surface water, then life might be much rarer than optimistic estimates suggest. Conversely, if Earth-like conditions are common, life could be widespread. Venus provides a crucial data point, a planet similar in size and composition to Earth, orbiting slightly closer to its star that became uninhabitable. How common is this outcome? Do most planets closer than Earth end up like Venus? Or was Venus somehow exceptional? Recent modeling studies suggest that the inner edge of the habitable zone, the boundary inside which runaway greenhouse effects occur, may be quite sharp. Small changes in stellar flux can push a planet from habitable to Venus-like. This has implications for planets orbiting red dwarf stars, the most common stars in the galaxy. Many rocky exoplanets have been found orbiting in the habitable zones of red dwarfs, but red dwarfs are cooler than the Sun, so habitable zone planets orbit much closer to their stars. These planets likely experience tidal locking, where one side perpetually faces the star and the other is in permanent darkness. The day side could experience runaway greenhouse conditions, even if the night side remains frozen. Understanding how Venus-like conditions develop helps us predict which exoplanets are truly habitable. The discovery of Venus-sized exoplanets orbiting very close to their stars, receiving far more stellar flux than Venus receives from the Sun, confirms that hot, Venus-like worlds are common. These planets almost certainly have thick atmospheres, dominated by CO2 or other heavy gases, with surface temperatures exceeding 1000 Kelvin. They're laboratories for studying extreme atmospheric physics and chemistry. Some may have lava oceans at their surfaces where rocks melt and vaporize, creating atmospheres of rock vapor. These extreme examples help us understand the limits of planetary atmospheres and the transitions between solid, liquid, and gas phases under extreme conditions. Venus also teaches us about planetary evolution over billions of years. Planets don't remain static. They evolve as their stars age and brighten, as their interiors cool, as volcanism and tectonics reshape surfaces, and as atmospheres change composition. Venus may have been habitable early on, then transitioned to uninhabitable as conditions changed. This evolutionary trajectory is relevant for understanding how planets change over time and for identifying the critical factors that determine long-term habitability. One implication is that habitability is not permanent. A planet can be habitable for a period and then lose that habitability through natural processes. This has philosophical implications for the search for life. If habitability is transient, life might arise on many planets but subsequently go extinct when conditions deteriorate. The universe could be full of dead planets that once hosted life. Alternatively, life might adapt and persist even as conditions worsen, retreating to refugia or evolving to tolerate more extreme environments. Understanding Venus's history helps us appreciate these possibilities. Earth's future is also relevant. Our sun is gradually brightening as it ages. Over the next billion years, solar luminosity will increase by about 10%. This will push Earth closer to the inner edge of the habitable zone. Eventually, perhaps in 1 to 2 billion years, Earth will begin to experience the runaway greenhouse process that Venus underwent. Our oceans will evaporate, hydrogen will escape to space, and Earth will become uninhabitable. This is a natural consequence of stellar evolution and is ultimately unavoidable. However, the timescale is so long that it's not a practical concern for humanity or Earth's biosphere on any foreseeable horizon. Our species and civilization will face many other challenges long before the sun's brightening becomes problematic. Nonetheless, the Venus scenario reminds us that planetary habitability depends on a delicate balance. Earth currently sits in the sweet spot where liquid water can exist, temperatures are moderate, and life flourishes. This state is maintained by various feedback mechanisms, including the weathering carbonate cycle, which regulates atmospheric CO2. If these mechanisms were disrupted, Earth's climate could potentially shift toward a new equilibrium that might be less hospitable. While we're not in immediate danger of becoming Venus, understanding how Venus became uninhabitable informs our understanding of Earth's climate system and the factors that keep our planet habitable. Venus is also relevant for thinking about planetary engineering or terraforming. Some have proposed that Venus could be made habitable through deliberate intervention, removing or sequestering the CO2 atmosphere, introducing water, establishing a stable climate. These proposals face enormous technical challenges. The mass of Venus's atmosphere is about 90 times Earth's atmospheric mass. Removing or converting that much CO2 would require energy and resources far beyond current capabilities. Even if we can reduce the greenhouse effect, Venus would still be extremely hot due to its proximity to the Sun. Cooling the planet would require shading it from solar radiation or increasing its albedo, perhaps by placing sunshades in orbit or engineering highly reflective clouds. Some more modest proposals suggest that we could create habitable zones in Venus's atmosphere rather than trying to terraform the entire planet. Floating habitats or colonies at 50 kilometers altitude, where temperatures and pressures are Earth-like, could be suspended in the CO2 atmosphere. These sky cities would require energy, probably from solar panels, and would need to manufacture or import resources. But atmospheric habitats might be more feasible than surface habitats, given Venus's extreme surface conditions. Whether such projects will ever be attempted is uncertain, but they represent one vision of humanity's possible future expansion beyond Earth. The study of Venus thus extends beyond pure scientific curiosity. It informs our understanding of how planets work, where habitability is possible, what went wrong on Venus, and what went right on Earth, and how planetary climates evolve over time. Every mission to Venus, every new measurement, every refined model contributes to this understanding. Venus is not just a hostile neighbor, but a crucial piece of the puzzle of planetary science, one that helps us contextualize Earth's place in the universe and understand the conditions necessary for life. Venus also teaches us about planetary interiors. Understanding how Venus loses heat without plate tectonics informs our understanding of other stagnant lid planets, including Mars and many exoplanets. The role of mantle plumes, lithospheric overturn, and hotspot volcanism in planetary cooling is relevant beyond Venus. The interior structure and evolution of rocky planets depend on their size, composition, and cooling mechanisms. Venus provides a key data point for testing models of planetary geodynamics. There's a sobering aspect to Venus's story. If Venus once had life, that life is gone, extinguished when conditions became too extreme. Life on Earth has survived numerous mass extinctions, ice ages, impacts, and climate changes. But there are limits to adaptation. If Earth's climate were to change dramatically enough, life might not survive. Venus reminds us that planets are not inherently hospitable. Habitability is a state that must be maintained, and once lost, it may be irretrievable. At the same time, Venus demonstrates the incredible diversity of outcomes possible for planets. From similar starting conditions, Earth and Venus evolved into starkly different worlds. The factors that determine which path a planet follows are complex, and sometimes depend on seemingly small differences. This diversity suggests that the universe may contain many types of worlds, each with its own unique history and characteristics. Understanding this diversity is essential for understanding our place in the universe. Looking forward, the exploration of Venus will continue to yield insights about planetary processes, climate evolution, and the conditions necessary for life. Each mission adds to our knowledge, revealing new details and raising new questions. The coming decade will be particularly exciting, as multiple spacecraft return to Venus, equipped with modern instruments far more capable than those on previous missions. Venus is a reminder of what might have been and what could have been lost. It's a world that started with potential but ended in catastrophe. It challenges us to understand not just what went wrong on Venus, but what went right on Earth, and how we can preserve the habitable conditions we've inherited. Venus is Earth's twin in size and composition, but its evolutionary path diverged from ours in the most dramatic way possible. Studying Venus helps us understand Earth, appreciate the uniqueness of our world, and recognize the factors that make life possible. It's a story of how planets can transform, a cautionary tale written in stone, and sulfuric acid clouds on the nearest planet beyond our own. If you've enjoyed this exploration of Venus, please consider liking this video and subscribing to the channel. Your support helps us continue creating these deep dives into space and the mysteries of our solar system. Until next time, keep looking up and wondering about the worlds that share our cosmic neighborhood. Good night, and sleep well knowing we live on the one planet among all those we've explored where the conditions aligned just right to make our existence possible.